A spacecraft plummets into a swirling vortex of distorted stars and vanishes. In an instant, it emerges near a distant, alien world. This is not just science fiction fantasy. It is the promise of a wormhole, a theoretical tunnel through the very fabric of space and time. By the end of this journey, you will explore 50 incredible theories that transform this wild idea into a breathtaking scientific frontier. We will uncover how these cosmic shortcuts could be forged from the leftovers of the Big Bang, how they might be hiding in plain sight as dark matter, and whether stepping through one could send you back to meet your own grandparents. The universe holds doors to places beyond our reach, and the keys are written in the language of physics. What door would you choose to open first? The very first key to this cosmic map was drawn not by a science fiction writer, but by the greatest scientific mind of the 20th century. In 1935, Albert Einstein and his colleague Nathan Rosen were exploring the strange implications of his theory of general relativity, the idea that gravity is the curvature of space and time itself. Their calculations revealed something astonishing. Deep within the mathematical description of a black hole, the equations did not simply end at a point of infinite density. Instead, they opened up, suggesting a tunnel or a bridge could form, linking the space around one black hole to the space around another, far distant one. They called this structure an Einstein-Rosen bridge. Picture the universe not as a flat sheet, but as a flexible fabric. Now, imagine pinching two distant points of that fabric downward until they nearly touch. The bridge is the short tunnel connecting those two pinched locations. A more common analogy is to take a piece of paper, draw two dots far apart on it, then fold the paper so the dots align. Instead of traveling the long line across the page, you could push a pencil straight through the fold, creating a shortcut. The pencil hole is the bridge. At the time, this was seen as a fascinating but purely theoretical mathematical quirk. The equations allowed it, but the bridge they described was incredibly unstable. It would snap shut faster than light or anything else could possibly travel through it. It was a door that slammed the instant you touched the handle, a tantalizing blueprint for a shortcut that nature itself seemed to forbid. Yet that blueprint, scribbled in the margins of reality by Einstein and Rosen, became the foundation for every wormhole theory that followed. It proved the cosmos might be filled with hidden architecture, waiting for us to find the right tools to unlock it. That mathematical door slammed shut for decades, a beautiful idea locked away by the laws of physics themselves. The problem was gravity, the immense pull of a black hole or the intense curvature of the wormhole's throat would crush it closed in an instant. Think of that tunnel through the folded paper. Now imagine the paper is a powerful rubber sheet, snapping back to flat the moment you try to push through. For any traveler, the journey would end before it began with the catastrophic collapse of the bridge. A wormhole needed an architect, something to shore up the walls and hold the door open against the universe's relentless desire to seal it shut. This is where the story takes its most fantastical yet scientifically serious turn. In the late 1980s, physicists including Kip Thorne and Michael Morris tackled this problem head-on. They asked what would it actually take, according to our known physics, to build a wormhole you could actually walk through. Their answer was both simple and utterly bizarre. To keep a wormhole stable and traversable, you would need to line its throat with a substance that possesses something called negative energy density. We often call this hypothetical material exotic matter. Now, what in the world is negative energy density? Let us break that down. Everything you see around you, from the air to the floor to your own body, has positive energy density. It weighs something. It exerts a gravitational pull, bending space-time inward like a weight on a mattress. This normal, positive gravity is what wants to crush a wormhole shut. Exotic matter would do the opposite. Instead of pulling space-time inward, it would push it outward. It would have a kind of anti-gravity effect, propping the wormhole's walls open like cosmic scaffolding. This is not antimatter, which still has positive gravity. This is something far stranger, a quantum ghost predicted to flicker in and out of existence at the smallest scales. In the bizarre realm of quantum field theory, empty space is not truly empty. It is a seething foam of virtual particles that pop into and out of existence for fleeting moments. Under certain extreme conditions, like between two incredibly close metal plates in a lab, this quantum foam can be manipulated to create a tiny, measurable amount of negative energy. This is the Casimir effect, a real phenomenon that gives us a whisper of proof that such exotic physics is possible. So the exotic matter needed for a wormhole is not a magic material we might mine from an asteroid. It is a specific, engineered state of a quantum field, a sustained region of repulsive gravity. The amount needed, according to Thorne and Morris's calculations, is astronomical. We are talking about the equivalent energy of an entire star or more, converted into this bizarre, space-repelling form. It is a staggering engineering challenge, one far beyond our current, or perhaps any, civilization's reach. Yet their work did something profound. It moved wormholes from the realm of pure mathematical curiosity into the domain of theoretical engineering. It gave us a blueprint, however daunting, for a machine that could, in principle, obey the laws of physics. The door was no longer permanently locked. We had found the key, even if we could not yet turn it. What other keys might be hidden in the quantum shadows of the universe? The most thrilling implication of a stable wormhole is not just crossing space, but crossing time itself. A traversable wormhole could, in theory, become a functional time machine. This hinges on a concept from relativity called a closed time-like curve. That is a complex term for a very simple idea. It is a path through space and time that loops back on itself, allowing an object to return to its own past. A wormhole provides the perfect structure to create such a loop. Here is how it could work. According to Einstein's theory, time is not a universal constant. It flows at different rates depending on gravity and speed. The stronger the gravity, or the closer you move to the speed of light, the slower time passes for you relative to someone in a weaker gravitational field or moving more slowly. This is not science fiction, it is proven fact. Our GPS satellites must account for these tiny time shifts to give you accurate directions. Now imagine our wormhole. It has two mouths, two openings in different parts of the universe. We leave one mouth, mouth A, parked safely near Earth. We take the other mouth, mouth B, and attach it to a super advanced spacecraft. That ship then accelerates to a significant fraction of light speed, travels on a long journey for a few years from its perspective, and returns to Earth. Because of time dilation, less time will have passed for the moving mouth and the travelers aboard. Let us say the journey took 5 years for the crew, but 10 years passed back on Earth. This is the classic twin paradox, where one twin travels at near light speed and returns younger than their sibling. But with a wormhole, the twist is profound. The two mouths are still connected by the instantaneous tunnel. The clocks at each mouth are now out of sync. Mouth B, after its journey, exists in Earth's present. But through the wormhole, it is connected to mouth as it was 5 years ago from mouth B's perspective. A traveler stepping into mouth B on Earth today would not emerge near the returning spaceship. They would step out of mouth A, 10 light years away perhaps, but also 10 years in the past, back when the journey began. You could walk through a door in 2024 and emerge in 2014. This creates staggering paradoxes. The most famous is the grandfather paradox. What if you traveled back and, by accident or design, prevented your own grandfather from meeting your grandmother? You would never be born, but if you were never born, you could not have traveled back to stop the meeting. So your grandparents would meet, you would be born, and the loop repeats. It is a logical contradiction that makes physicists deeply skeptical. The universe seems to have rules that prevent such paradoxes, perhaps through unknown quantum laws that would snap the wormhole shut the moment a paradox was attempted, or by allowing only self-consistent loops where your actions in the past were always part of history. The wormhole as a time machine is not just a ticket to the past, it is a challenge to our deepest understanding of cause and effect, a puzzle written into the fabric of reality itself. These paradoxes force us to confront a fundamental question. If exotic matter is so rare and strange, could wormholes ever be more than a theoretical blueprint? Perhaps the answer lies not in the vastness of space, but in the bizarre, flickering emptiness of the quantum world. There is a real laboratory phenomenon that gives us a tiny, measurable glimpse of the exotic physics required. It is called the Casimir effect. To understand it, we must first accept that a perfect vacuum, true nothingness, does not exist. According to quantum field theory, empty space is a turbulent sea of virtual particles. These are not real particles you could catch, but fleeting fluctuations in energy fields. They spontaneously pop into existence as particle-antiparticle pairs, borrowing energy from the universe for an immeasurably brief moment before annihilating each other and paying the energy back. This chaotic dance is known as the quantum foam. Now, place two perfectly smooth, uncharged metal plates incredibly close together in this vacuum, separated by a gap smaller than the width of a virus. This setup creates a boundary. Only certain wavelengths of these quantum fluctuations can fit between the plates, while outside the plates all wavelengths are possible. This imbalance in the quantum activity creates a subtle pressure difference. The radiation pressure outside the plates becomes slightly greater than the pressure between them. The result, the plates are pushed together by an invisible force from the vacuum itself. This measured force is the Casimir effect. Why is this so revolutionary for wormholes? Because the region between those plates for that brief instant exhibits negative energy density. The quantum fields there are in a lower energy state than the surrounding empty space. This is exactly the kind of repulsive gravity, the exotic matter, that the equations say is needed to prop open a wormhole's throat. Of course, the amount generated in a lab is infinitesimally small. But it proves the principle is not magic. It is woven into the fabric of reality at the smallest scales. This leads to a breathtaking speculation. If the vacuum constantly boils with this quantum foam, and that foam can produce fleeting bits of negative energy, then could the universe be spontaneously generating wormholes all the time? Not the star-spanning tunnels of science fiction, but something far stranger. Theorists like John Wheeler proposed that at the Planck-scale, the smallest possible unit of length, space-time itself might be a chaotic froth. Within that froth, unimaginably tiny wormholes could be constantly forming, connecting, and pinching off in a frenzy of topological change. These would be smaller than a subatomic particle, lasting for fractions of a fraction of a second. They would be less like tunnels and more like ephemeral knots in the fabric of space-time itself. Our entire universe, on this view, might be built upon a seething foundation of microscopic wormholes, blinking in and out of existence like foam on a quantum sea. If we could somehow stabilize one, coax it open and feed it energy, could we grow a traversable wormhole from a quantum seed? The Casimir effect does not give us a wormhole engine. It gives us a whisper from the vacuum, a hint that the exotic ingredient we so desperately need is not just possible, but is happening right now in the emptiness between atoms. That quantum foam hints at wormholes born from the universe's chaotic infancy, but another relic from that same explosive birth might offer a more solid foundation. Cast your mind back to the first fraction of a second after the Big Bang, when the cosmos was an unimaginably hot, dense soup of energy and forces. As it expanded and cooled, the fundamental forces of nature separated out from one another like water freezing into ice. Physicists theorize that this phase transition might not have been perfectly smooth. Cracks could have formed in the very structure of space-time itself. These cracks are known as cosmic strings. They are not strings in the everyday sense. Imagine a flaw in a crystal, a line where the atomic structure is misaligned. A cosmic string is a one-dimensional defect in the fabric of the universe, a thread of pure energy left over from creation. They are theorized to be thinner than a proton, yet so incredibly dense that a single inch of one could have the mass of an entire mountain range. They would stretch across the cosmos for light years, vibrating like ultra-dense guitar strings, and their immense gravity would lens light from stars behind them, creating telltale double images in the sky. While we have suggestive hints, no cosmic string has ever been conclusively observed. But if they do exist, they could be the ultimate cosmic construction material. The theory goes like this: the gravity of a cosmic string is so intense that it warps spacetime into a sharp cone around it. Picture a pencil pushing down into a rubber sheet. Now take two such pencils, two cosmic strings, and move them past each other at a significant fraction of the speed of light. The combined dynamic warping of spacetime from these two ultra-dense, ultra-fast-moving objects could be so severe that it might stitch their individual gravitational fields together, twisting the fabric of reality into a loop. This twisted region, under the right conditions, could theoretically open a shortcut, a wormhole connecting two distant points that the strings themselves link. It is a bit like dragging two incredibly heavy weights across a trampoline at high speed. If you cross their paths just right, the fabric might not just dip, but might momentarily tunnel through itself where the distortions overlap. The challenges here are almost beyond comprehension. First, we must find a cosmic string, a needle in a galactic haystack that may not even exist. Then we would need to find two of them, or perhaps manipulate one into a loop. Finally, we would need to move these objects, each with the mass of a solar system compressed into a thread, at relativistic speeds with perfect precision. The energy required is godlike, yet this theory offers something crucial. It suggests that wormholes might not require exotic matter we must manufacture. They might be built from the raw, hyper-dense materials the universe already forged in its first moments. They would be cosmic engineering on the grandest scale, using the universe's own scars as scaffolding. If such strings are real, they are not just fossils. They are the hidden girders in the architecture of everything, and their silent, high-speed dance could be weaving tunnels we have yet to see. The universe's architecture might be woven from threads we have only just begun to see. One of the most profound and radical ideas in modern physics suggests that the deepest connection in the cosmos is not a force, but a link between two seemingly unrelated concepts. On one side, we have wormholes, the Einstein-Rosen bridges born from gravity's grip on spacetime. On the other, we have the spooky phenomenon of quantum entanglement, where two particles become so deeply linked that measuring the state of one instantly determines the state of the other, no matter the distance separating them. For decades, these were entirely separate chapters in the book of physics, one describing the vast cosmic stage, the other describing the bizarre backstage rules. Then, a revolutionary conjecture emerged known as ER equals EPR. The letters are a code. ER stands for Einstein and Rosen, the pioneers of the wormhole. EPR stands for Einstein, Podolsky, and Rosen, the physicists who first highlighted the strange paradox of entanglement. The equal sign in the middle is the breathtaking leap. Proposed by physicists Juan Maldacena and Leonard Susskind, the idea is this: what if an Einstein-Rosen bridge, a microscopic wormhole, is not just like quantum entanglement but is the same thing physically? What if two entangled particles are not communicating faster than light through some invisible field, but are actually connected by an unimaginably tiny tunnel through the fabric of spacetime itself? Think of it this way: you have two magical coins, one on Earth and one on a planet orbiting a star 1,000 light-years away. You flip them, and they always land on the same face instantly. The old explanation was a mysterious, instantaneous link. The new AR=EPR picture suggests there is a thread, a physical tunnel too small to travel through, but real, stitching those two coins together across the vast distance. The entanglement is the wormhole. This idea transforms our understanding of reality. It implies that the fabric of space and time, the very stage upon which the universe plays out, might be built from a vast cosmic web of quantum entanglements. Every connection between particles is a stitch in the quilt of spacetime. Where entanglement is dense and complex, space is born. Where it is absent, space ceases to have meaning. This provides a potential bridge, a wormhole in thinking itself, between the two great pillars of modern physics that have stubbornly refused to unite. Einstein's theory of gravity describes space and time as a dynamic, curving geometry. Quantum mechanics describes particles and forces through probabilities and connections. AR=EPR hints that geometry comes from connection. The gravity we feel and the quantum links we observe could be two faces of the same deeply hidden reality. If this is true, then every entangled pair in the universe, from particles in a lab to those in distant stars, is quietly hosting a microscopic wormhole, a pinprick in the cosmos binding it together. The largest structures we see might be built from the smallest possible stitches. The idea that spacetime might be woven from quantum threads is staggering, but what if we could twist the fabric of the cosmos with a machine of our own design? Another avenue for bending time into a loop exists, one that does not require a tunnel at all, but a spinning vortex of unimaginable mass. This is the concept of the Tipler cylinder, sometimes called a Roman ring after the physicist Frank Tipler, who explored its potential. Imagine a cylinder, but not one made of steel or any known material. This cylinder would need to be infinitely long and composed of something with the density of a neutron star compressed into a perfect solid form. Then set it spinning, not just spinning quickly, but rotating at a significant fraction of the speed of light. According to Einstein's equations, such an object would do more than just occupy space. Its immense mass and furious rotation would drag the very fabric of spacetime around with it, like a spoon stirring a thick fluid. This effect is known as frame dragging, and we have observed it in a subtle form around our own rotating Earth. But around a Tipler cylinder, the dragging would be so extreme that spacetime would not just twist, it would tie itself into knots. The twisted region around the cylinder could create closed time-like curves, paths that loop back on themselves. If you were to pilot a spacecraft on a carefully calculated spiral orbit around this spinning cosmic pillar, you could, in theory, follow a path that leads you back to a point in your own past. You would not be traveling through a tunnel, but navigating a corkscrew in the continuum itself, arriving back at your starting point before you ever left. It is a time machine built from pure motion and gravity. Yet, the requirements instantly reveal why this remains a thought experiment. First, the cylinder must be infinitely long. Any finite cylinder, according to the math, would not produce stable closed time-like curves. The ends would disrupt the delicate spacetime geometry needed. Second, the material needed to construct it would have to be impossibly dense and strong, likely requiring some form of exotic matter to prevent it from collapsing under its own gravity into a black hole. We are talking about a structure that defies both engineering and known physics. So why do physicists still ponder it? The Tipler cylinder serves as a crucial stress test for our theories. It shows that general relativity, in its pure mathematical form, does not strictly forbid time travel. The prohibition seems to come not from the equations of gravity, but from the practical and quantum mechanical constraints of the universe. It is a signpost pointing to a deeper law we have yet to fully articulate, a cosmic censorship that may prevent such paradoxes from ever forming. The cylinder is a ghost in the machine of relativity, a reminder that the universe's rules are often written in the fine print. The ghost of the Tipler cylinder shows us the universe's rules are often hidden in the fine print of reality. But there is another cosmic object where the fine print becomes a screaming contradiction, a place where our understanding of physics breaks down completely. This brings us to a persistent and powerful image from science fiction, the idea of a black hole as a gateway. The visual is iconic, a spacecraft plunging into the inky darkness of an event horizon, only to emerge light years away through a wormhole. It is a compelling shortcut, but is it rooted in real theory, or is it a beautiful misunderstanding? To untangle this, we must return to the very first wormhole ever described, the Einstein-Rosen bridge. You will recall this was the mathematical tunnel that appeared in the equations describing a simple, non-rotating black hole, what physicists call a Schwarzschild black hole. The bridge did not lead out of our universe. According to that pure mathematical solution, it connected the black hole's interior to something utterly bizarre, a white hole in another universe entirely. A white hole is the theoretical time reversal of a black hole. Where a black hole's event horizon is a point of no return, a one-way door inward, a white hole's horizon would be a point of no entry, a one-way door outward. Nothing could ever fall into a white hole, but matter and energy could explosively pour out of it. So the classic Einstein-Rosen bridge model suggests that if you fell into this specific type of black hole, you would not be crushed at the center. Instead, you would pass through the wormhole throat and be ejected from the white hole into a completely different cosmos. This sounds exactly like the science fiction gateway. But here is the critical catch that makes it non-traversable in any practical sense. The journey is not a smooth tunnel ride. First, the wormhole inside this black hole is incredibly unstable. It would collapse faster than you could pass through it. Second, and more fundamentally, to even reach the region where the bridge exists in the mathematics, you must first pass through the black hole's singularity, the point of infinite density at its core. Our laws of physics provide no description of what happens at a singularity. It is not a place, it is a breakdown in the map. Space and time cease to have any sensible meaning there. In any realistic scenario, long before you could access the theoretical wormhole, you would be torn apart by unimaginable tidal forces, a process physicists grimly call spaghettification. Your atoms would be stretched into an infinitely thin stream. So while the wormhole geometry is mathematically present in the description of a simple black hole, it is completely inaccessible. It is like having a detailed map of a beautiful island, only to discover the map is locked inside a bank vault at the bottom of an active volcano. The information is there, but you can never use it. This starkly contrasts with the traversable wormholes we discussed earlier, the ones lined with exotic matter. Those are engineered structures, theoretically stable tunnels that bypass the horrors of a singularity entirely. They are like building a reinforced subway beneath a mountain, rather than trying to walk through the mountain's molten core. The black hole gateway of popular culture is a dramatic simplification. It takes a kernel of mathematical truth, the Einstein-Rosen bridge, and strips away the lethal, universe-breaking physics that make it a one-way trip to oblivion, not a portal to the stars. The real cosmic shortcuts, if they exist, are not found in the destructive hearts of black holes, but in the delicate, propped-open tunnels we might one day learn to build or find elsewhere in the cosmos. That lethal journey through a black hole's heart hints at a destination stranger than any alien world. If the classic Einstein-Rosen bridge is real, then falling into one end might not be the end of the story. You could, in theory, be violently expelled from the other side. This brings us to the ghost in the mirror of a black hole, the white hole. A white hole is exactly what its name suggests, the opposite of a black hole in every way. While a black hole's event horizon is a one-way membrane you can fall into but never escape, a white hole's horizon is a one-way membrane you can never enter. Nothing, not even light, can cross its boundary from the outside, but from the inside, matter and radiation can only pour outward in a relentless, explosive eruption. It is a cosmic fountain of energy with no visible source, a region of spacetime that refuses to accept anything, only to give. in the context of wormholes, the white hole becomes the logical exit. Picture the simplest wormhole model again, the Einstein-Rosen bridge connecting a black hole in our universe to a white hole in another. The black hole is the entrance, the point of no return. The white hole is the exit, the point of no entry from the other side. Anything that miraculously survived the trip through the tunnel would not be able to turn around and go back the way it came. The white hole would violently repel it, sealing that direction forever. This creates a profoundly one-way trip. You step into the black hole entrance here, and you are vomited out of the white hole exit somewhere else with no possibility of return through the same passage. It is the ultimate cosmic dead-end street. So why have we never seen a white hole? Most physicists consider them to be wildly speculative and almost certainly unstable. The problem is thermodynamics, the laws governing energy and disorder. A white hole, by its very definition, would violate the second law of thermodynamics if it formed in our universe from ordinary collapse. It represents a decrease in entropy, a reversal of the universal trend toward disorder. Furthermore, any attempt to form a white hole from collapsing matter would likely be instantly overwhelmed by the very material and energy trying to explode out of it. The slightest bit of external matter falling onto its horizon would, according to some calculations, cause it to collapse immediately into a black hole. Think of it like trying to keep a geyser erupting forever in a rainstorm. The moment any of the falling rain touches the erupting water, the entire delicate balance shatters. For a white hole to exist as a stable exit, it would need to exist in a pristine region of spacetime with absolutely nothing around it, not even stray atoms of hydrogen or the faint glow of cosmic background radiation. Our universe is far too cluttered for such purity. So while white holes are a mathematically elegant counterpart to black holes in the equations of general relativity, they are almost certainly not permanent features of our cosmos. They might flicker into existence for the briefest instant at the end of a wormhole's life, or exist only in other universes with different physical laws. In the grand wormhole picture, they serve as a reminder that not all cosmic doors swing both ways. Some tunnels are built for exile, offering a journey to a place you can never leave, ejected into a reality where the way home was sealed behind you the moment you arrived. White holes offer a one-way trip into cosmic exile, but what if we could build a round-trip ticket? The most famous blueprint for such a journey is the Morris-Thorne wormhole, a specific, elegant solution to Einstein's equations that describes a tunnel you could actually pass through. Named for physicists Michael Morris and Kip Thorne, this model provides the clearest picture we have of what a traversable wormhole might actually be. It is not a chaotic, collapsing bridge inside a black hole. Instead, imagine a perfectly smooth, spherical entrance floating in space, like a shimmering soap bubble the size of a planet. This is the mouth of the wormhole. Step through, and you would find yourself inside a throat, a tunnel of curved space that remains at a constant width, held rigidly open against the crushing force of gravity. This is the critical feature. The Morris-Thorne wormhole is spherically symmetric and static, meaning it looks the same from all angles and does not change over time. It is a piece of cosmic infrastructure, a permanent subway station built into the fabric of reality. For this station to stand, two non-negotiable engineering requirements must be met. First, the throat must have a minimum radius, perhaps a kilometer or more, and this entire inner surface must be lined with a shell of exotic matter. This is the negative energy density material we discussed earlier, acting as cosmic scaffolding to push the walls outward, preventing the tunnel from pinching shut. Second, the curvature of space within the throat must be gentle enough for a human traveler. If the tunnel is too small or too sharply curved, the difference in gravity between your head and your feet, the tidal forces, would become extreme. You would be stretched like taffy, so the wormhole must be large and smooth, its geometry carefully tuned to be survivable. Now, let us take that journey. You approach the spherical mouth. From the outside, it might look like a perfect mirror reflecting a distorted view of the stars behind you, or perhaps a window showing a swirling, inverted image of the destination. As you cross the threshold, there is no sudden jolt, no flash of light. You are simply inside. The throat around you is not a dark tube with walls of rock. You are surrounded by curved space itself. If you looked back the way you came, you would see the mouth you entered, now a shrinking circle of light, but the view through it would be bizarrely compressed, showing your entire point of origin folded into a tiny disk. Looking forward, you would see the exit mouth growing larger, but the view through it would be equally distorted, a fisheye lens showing the entire destination star system. The journey through the throat might take only seconds, as the distance through the wormhole could be mere hundreds of meters, while the distance through normal space is thousands of light years. You walk or float through this corridor of warped geometry, and then you step out. The exit mouth is behind you now, a similar shimmering sphere hanging in an alien sky. You have not traveled through space in the conventional sense. You have taken a shortcut through the folded map of the universe. The Morris Thorne model gives us more than a mathematical curiosity. It gives us a sense of scale, a list of parts, and a haunting vision of what stepping through a cosmic door might truly feel like. It turns a wild dream into a theoretical schematic, waiting in the equations for someone or something to begin construction. Stephen Hawking looked at these theoretical blueprints for time machines and declared the universe would never allow them. He proposed a powerful, if frustrating, idea called the chronology protection conjecture. In essence, Hawking bet that the laws of physics contain a built-in safety mechanism, a cosmic rule that prevents time travel to the past. He argued that if someone tried to create a closed time-like curve, the universe itself would step in to stop it. Think of it as a fundamental failsafe, a law of reality that protects the sequence of cause and effect from paradox. Hawking famously said the absence of tourists from the future is a strong argument that time travel is impossible. But his conjecture goes deeper than a simple observation. It proposes a specific physical mechanism for how chronology gets protected. The villain in this story is the quantum vacuum, that seething foam of virtual particles we met earlier. In normal, flat spacetime, these particle pairs pop in and out of existence everywhere, their effects averaging out to zero. But in the severely warped geometry of a near-time machine, like the region just forming inside a wormhole throat, this delicate balance breaks down catastrophically. As a wormhole is tuned to become a time loop, the paths of these virtual particles can become twisted into feedback loops. A single virtual particle could travel back in time an instant, interact with its earlier self, and then travel back again, creating an infinite cycle. In the equations, this doesn't just create a little extra energy. It causes a runaway effect called vacuum polarization, where the energy density of these quantum fluctuations builds without limit, spiraling toward infinity. This infinite energy surge would act like a bomb at the heart of the wormhole. Just as the tunnel was about to become a gateway to yesterday, the escalating quantum feedback would tear space-time apart, collapsing the wormhole into a singularity or simply vaporizing it. The universe, according to this idea, would rather destroy a region of itself than allow a paradox to form. It's a dramatic form of cosmic censorship. You can approach the threshold of time travel, you can fiddle with the dials, but the moment you cross the line, physics itself intervenes with overwhelming force. Hawking's principle doesn't say wormholes to other places are impossible. It specifically targets the ones that could become loops to the past. The conjecture remains unproven, a bold bet on nature's design. Yet it offers a profound comfort. It suggests that the flow of time we experience isn't a fragile accident, but a deeply protected feature of reality, guarded by the most fundamental laws we know. Hawking's cosmic censorship protects the timeline from paradox, but it leaves a profound mystery untouched. Across the universe, galaxies spin too fast, and clusters of galaxies hold together with more gravity than their visible stars can provide. Something invisible, something that does not emit or reflect light, is holding the cosmos together. We call this ghostly presence dark matter. For decades, physicists have searched for exotic particles that could explain it. But what if the answer is not a particle at all? What if dark matter is not a new form of matter, but an ancient form of architecture? This is a bold and elegant theory that the missing mass of the universe could be a vast, unseen population of wormholes. Not the star-spanning tunnels of our dreams, but something far smaller and more numerous. Imagine the universe in its first fiery moments after the Big Bang, a seething, turbulent cauldron of energy. In that chaos, as space-time itself crystallized from a quantum foam, trillions upon trillions of microscopic wormholes could have been forged like bubbles frozen into ice. These would be primordial wormholes, relics of creation, each one smaller than an atomic nucleus. They would not be lined with exotic matter or be traversable by any conceivable being. They would simply be topological knots in the fabric of space, permanent tiny tunnels connecting two points that may be light years apart or mere millimeters. Because they are so small and do not interact with light, they would be utterly invisible, but they would possess mass. The energy required to twist space into these knots, locked into their structure, would give them a gravitational footprint. A single one would be negligible, but if they were as common as the theory suggests, sprinkled like cosmic dust through every galaxy and halo, their combined gravitational pull could be immense. They would act exactly like dark matter, weaving an invisible gravitational web that guides the motion of stars and binds galaxies together without ever being seen. This idea transforms dark matter from a cloud of unknown particles into a hidden landscape of spacetime itself. It suggests the universe is not just filled with matter, but is threaded through with microscopic shortcuts, a fractal lacework of tunnels left over from its birth. How could we ever hope to detect such a thing? The key is gravity's effect on light, a phenomenon called gravitational lensing. We know that massive objects like galaxy clusters bend the path of light from more distant stars, acting as a cosmic magnifying glass. A swarm of microscopic wormholes would create a specific, subtle signature. As a distant star's light passes through the halo of our galaxy, it would not be bent smoothly by a diffuse cloud of particles. Instead, the light would occasionally flicker or twinkle as it passed near the intense, pinprick gravity of an individual wormhole knot. It would be like looking up at a streetlight through a shower of falling rain. Each raindrop acts as a tiny lens, creating a complex, shimmering pattern. Astronomers are already designing searches for such microlensing events caused by other compact objects. If they began to find a specific, unexplained pattern of flickers that cannot be accounted for by stars, planets, or black holes, it could point to this ghostly population of spacetime knots. Finding them would be more than solving the dark matter puzzle. It would be discovering that the universe's hidden skeleton is built from wormholes, a breathtaking connection between the largest mystery in cosmology and the smallest twists in the quantum fabric of reality. The dark matter that binds galaxies could be woven from ancient spacetime threads, but to find them we must look deeper into the very foundation of reality. At the smallest imaginable scale, the smooth, continuous universe we perceive dissolves into chaos. This is the realm of the quantum foam, a concept pioneered by physicist John Wheeler. If we could zoom into the Planck length, a distance so tiny that 1 trillion of them could fit across a single proton, the fabric of spacetime would not look like a calm sheet. It would look like a turbulent, boiling sea. Here, the concepts of here and there, before and after, lose their meaning. The geometry of the universe itself is subject to quantum uncertainty, constantly fluctuating. In this frenzied foam, the energy of the vacuum spontaneously creates not just particle pairs, but entire microscopic structures. tiny loops of spacetime can pinch off, forming fleeting, self-contained baby universes. More relevant to our journey, minuscule wormholes are constantly bubbling into existence, connecting two random points in this quantum frenzy for an infinitesimal moment before pinching shut and vanishing back into the energetic haze. These are virtual wormholes, as ephemeral as the virtual particles of the Casimir effect. They are not tunnels you could see or travel through. They are more like temporary knots in the fabric, topological hiccups governed by the Heisenberg uncertainty principle. They borrow energy from the vacuum for a duration so brief it is almost non-existent, then repay it by disappearing. This is not a metaphor. It is a direct prediction of marrying quantum mechanics with our understanding of gravity. The foam is what spacetime is at its most fundamental level. Our entire smooth, classical universe emerges from this quantum chaos, like the calm surface of the ocean emerging from the frantic motion of countless molecules. Now, a staggering possibility emerges from this foam. What if the traversable wormholes of our grandest dreams begin their existence here in this quantum frenzy? The challenge of building a wormhole from scratch, of assembling exotic matter and bending spacetime on stellar scales seems insurmountable. But what if we did not have to build one from nothing? What if we could instead find one in its embryonic virtual state and nurture it? This is the ultimate speculative engineering project, mastering a theory of quantum gravity. The long-sought unification of Einstein's relativity with quantum mechanics might give us the tools to interact with the foam itself. Imagine a technology far beyond our own that could somehow probe this Planck-scale chaos, detect the brief flicker of a virtual wormhole as it forms, and then inject energy into it at precisely the right moment and in precisely the right way. The goal would be to prevent it from vanishing, to feed it, to stabilize its structure with exotic matter, and to coax it to grow larger, from a quantum knot smaller than a quark to a macroscopic tunnel one could step through. It would be like finding a microscopic seed in a stormy ocean, and with unimaginable precision, providing it the exact conditions to grow into a mighty redwood. The energy required would still be astronomical, and the control needed over quantum geometry is far beyond our current comprehension. Yet, this theory offers a profound shift in perspective. It suggests that wormholes may not be rare, distant objects we must find in deep space. They may be all around us and within us, trillions of them flashing into and out of existence every second at a scale our senses cannot perceive. The gateway to the stars might not be out there. It might be right here, woven into the quantum fabric of the empty space in this room, waiting for a hand steady enough to grasp a thread from the foam. The quantum foam hints at wormholes born from nothing, but some of the most violent events in the cosmos might forge them from pure destruction. We have entered an era where we can feel the universe shake. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, has given us ears to listen to spacetime itself. It has heard the final, spiraling dance of two black holes as they collide and merge, sending ripples through the fabric of reality that we detect as gravitational waves. These cosmic crashes are the most energetic events since the Big Bang, warping spacetime with unimaginable ferocity. A compelling theory suggests that in the final, chaotic moment of such a merger, something more than a simple black hole might form. For an instant, the two singularities might not just combine. The violent, dynamic twisting of the geometry could stitch their horizons together into a different shape entirely, a short-lived bridge, a wormhole. This would not be a stable, traversable tunnel. It would be a transient throat, a cosmic spasm born from the collision of two infinities. The newborn object would be highly unstable, likely collapsing almost immediately into a single, larger black hole. But for that fleeting moment, a passage through the bulk of spacetime could exist. The question is, could we ever hear evidence of such a thing in the data? Physicists propose looking for an echo. When two black holes merge, the gravitational wave signal we receive has a very specific pattern. There is the rising chirp as they spiral inward, then a loud peak at the moment of merger, followed by a series of fading ripples called the ringdown as the new, single black hole settles into its final, quiet shape. If a wormhole throat formed instead of a classic event horizon, the story would be different. A wormhole throat is not a one-way membrane, it is a two-way passage. Some of the gravitational wave energy, the vibrations of spacetime, could bounce between the two mouths of this short-lived bridge before escaping. This would create a faint, repeating echo in the signal after the main merger peak, like a sound reverberating in a cavern. LIGO and other observatories are now listening for these subtle echoes hidden in the ringdown data. Finding one would be a discovery of monumental proportions. It would mean that the most destructive events in the universe are not just making black holes, they are momentarily bending the rules, creating topological shortcuts that flicker and die in the same instant. It would be a direct, observational hint that wormhole geometry is not just a mathematical fantasy, but a real, physical possibility etched into the most extreme events nature can produce. Each new gravitational wave detection is not just a recording of a crash. It is a listening session at the edge of creation, waiting to hear the whisper of a tunnel that defies the map. Gravitational waves may echo with the ghosts of fleeting tunnels, but what if a shortcut could be paved like a cosmic highway, one stretch at a time? This is the promise of the Krasnikov tube, a different kind of theoretical shortcut that trades the instant connection of a wormhole for a more methodical and perhaps more plausible form of engineering. Proposed by physicist Sergei Krasnikov, this concept is less a door through folded space and more a prepared track where the rules of the journey are rewritten. Imagine an advanced civilization that wishes to establish a reliable route between two stars. They do not search for a pre-existing wormhole, instead they build one. A single pioneering spacecraft embarks on the long, slow journey from Earth to a distant star system using conventional propulsion. This voyage might take centuries. But as it travels, this ship does something extraordinary. It uses an immense onboard energy source to permanently alter the spacetime along its precise path. It warps the fabric of the universe along this narrow, tube-like corridor, creating a region where the speed of light, the ultimate cosmic speed limit, is effectively higher. Think of it not as punching a hole through a mountain, but as laying down a stretch of magical railroad track where trains can travel at impossible speeds. Once the ship reaches its destination, the work is complete. The path is now a prepared tube, a subway tunnel through curved spacetime. The crucial feature is this. The return trip through this tube takes almost no time at all. A second ship, leaving Earth after the tube is built, can enter this prepared corridor and zip to the distant star in a subjective instant because the space within the tube has been preconditioned for ultra-fast travel. It is a one-way superhighway that must be constructed the slow way first. How does this differ from a classic wormhole? A wormhole is an instantaneous connection, a door linking two distant points directly. Step in here, step out there, with no travel time through the tunnel itself. The Krasnikov tube, however, is a path. You must still travel the entire distance between the 2 points, but you do so within a corridor of altered physics that makes the trip effectively instantaneous for the traveler. It is the difference between taking a helicopter directly to the top of a mountain versus riding a supersonic train up a track that spirals around it, a track that had to be painstakingly built by someone who first hiked up the slow way. This idea shares some DNA with the Alcubierre warp drive, another concept where a ship rides a wave of contracted and expanded spacetime. But the Krasnikov tube is not a bubble moving with a ship. It is a fixed piece of cosmic infrastructure left behind for others to use. The implications are fascinating for an expanding interstellar civilization. The first colony ship to a new star makes the great generations-long sacrifice. But its mission is not just to deliver colonists, it is to pave the way, to build the permanent highway home and for all who follow. This transforms interstellar exploration from a series of isolated, one-way voyages into the construction of a connected network, a subway map of the galaxy drawn in the fabric of spacetime itself. The energy requirements remain stupendous, likely requiring the manipulation of exotic matter or dark energy on a scale we can barely conceive. Yet, it offers a different vision of our future among the stars, not as wanderers stumbling upon cosmic doors, but as engineers, patiently laying down the tracks for journeys our grandchildren will make in the blink of an eye. The tracks of a Krasnikov tube would be laid for a destination within our own universe, a star we can see on our maps, but the ultimate destination for a wormhole might not be on any map we could ever draw. If the classic Einstein-Rosen bridge is more than a mathematical ghost, it points to a conclusion that reshapes reality itself. Falling into a black hole through the wormhole throat, you would not emerge in another part of our cosmos. The equations suggest you will be expelled from a white hole, a point of no entry in a completely different universe altogether. This is not just intergalactic travel. This is exodus to another creation. The wormhole becomes a one-way door out of everything we know, into a separate cosmic realm with its own history, its own stars, and perhaps its own utterly alien laws of physics. This idea is the cornerstone of one of the most profound theories in modern cosmology, the multiverse. Our universe, in this view, is not alone. It is one bubble in a vast, frothing sea of universes, each with its own unique properties. Wormholes provide a potential physical mechanism for how these bubbles could connect or how new ones are born. Imagine our universe as a giant, expanding balloon. Now picture a tiny, microscopic wormhole forming on its surface. Under the right conditions of extreme gravitational pressure, like near a black hole singularity, that wormhole's throat could pinch off and seal itself from our side. But what happens to the other end? It could inflate on its own, driven by a burst of repulsive gravity, blossoming into a whole new, self-contained spacetime balloon, a baby universe. This newborn cosmos would be connected to its parent by a cosmic umbilical cord that has now been severed, floating away into its own dimensional space. This is not just wild speculation. It finds a home within the framework of cosmic inflation, the theory that our universe underwent a period of hyper-fast expansion just after the Big Bang. In an eternally inflating multiverse, new bubble universes are constantly budding off from the inflating background, like bubbles forming in a pot of boiling water. A wormhole could be the stalk from which such a bubble grows. This concept dovetails with string theory's landscape, which suggests there are perhaps 10 to the 500 different possible stable configurations for the laws of physics. Each bubble universe could crystallize with a different random set of those laws. In one, gravity might be 1,000 times stronger. In another, electromagnetism might not exist, and chemistry as we know it would be impossible. A wormhole, then, could be a gateway to a realm where matter is unrecognizable, where time flows backward, or where the constants of nature are set to values that make life as we know it inconceivable. Stepping through would be the ultimate gamble, a journey into a reality where the very rules of existence are rewritten. It raises a haunting question. If such gateways exist, are they natural accidents of cosmic violence? Or could they be the carefully constructed portals of a civilization that learned to navigate the multiverse, sending probes or even themselves into new cosmic experiments? The wormhole is no longer just a shortcut. It is a genesis point, a tear in the canvas of our reality, leading to a canvas of an entirely different color. Spinning cylinders of infinite dust sound like a physicist's fever dream, yet they hold a key to twisting time. This is the Van Stockham dust solution, a cousin to the Tipler cylinder, but built from a different, equally impossible material. Imagine not a solid metallic pillar, but an infinitely long, perfectly straight cylinder composed entirely of a fine, swirling dust. Every single dust particle is in a state of perfect, synchronized rotation around the cylinder's axis, like a cosmic tornado frozen into a permanent, rigid structure. The mathematics of general relativity show that this specific configuration of mass and motion creates a gravitational field so extreme that it drags spacetime into a vortex around it. The faster the dust cylinder spins, the more severe the frame dragging becomes. At a certain critical rotational speed, something extraordinary happens. The twisted paths through spacetime around the cylinder close back on themselves, forming closed time-like curves. A spacecraft following a precise spiral orbit could, in theory, travel along a corkscrew path that loops back to an event in its own past. It is not traveling faster than light, but navigating a helical groove carved into the continuum by the cylinder's spin. Now, embed a wormhole into this swirling maelstrom. Picture one mouth of a Morris Thorne wormhole placed at the center of this rotating dust cylinder, while the other mouth remains stationary in calm space. The intense, spinning gravitational field would affect the local flow of time at that moving mouth. Just as with the twin paradox wormhole time machine, this creates a time difference between the two connected points. But here, the time machine is not built by moving one mouth through space, but by placing it in a region of spacetime that is itself rotating at a relativistic pace. The vortex does the work. The result is the same, a gateway where walking in one side could send you out the other side at an earlier date. The engineering challenges, however, are even more surreal than the concept itself. First, the cylinder must be infinite. Any finite length would cause the delicate spacetime geometry to unravel at the ends, destroying the closed time-like curves. Second, the dust distribution must be perfectly uniform and maintain its coherent rotation without collapsing under its own gravity into a black hole or simply scattering. This requires a form of matter with zero pressure, a perfect, non-interacting dust that somehow coheres into an eternal, stable whirlwind. We are describing a ghostly architecture, a sculpture made of synchronized chaos that defies every known material science. The Van Stockum dust cylinder, like the Tipler cylinder, is less a blueprint and more a boundary marker. It shows us just how far the equations of gravity can be pushed before they break, revealing the outer limits of what spacetime might be forced to do under conditions so perfect they border on the metaphysical. That ghostly architecture of spinning dust reveals the extreme limits of our equations, but what if we have been looking at those equations through the wrong lens? The requirement for exotic matter, that repulsive scaffolding, has long been the single greatest barrier between wormhole theory and physical possibility. Yet a daring line of inquiry asks, what if we could build a traversable wormhole without it? What if the need for exotic matter is not a law of nature, but an artifact of our specific theory of gravity, Einstein's general relativity? This challenge has led physicists to explore modified theories of gravity, frameworks where the rules of spacetime itself are subtly rewritten. One of the earliest and most famous alternatives is Brans-Dicke theory, developed in the 1960s by Karl Brans and Robert Dicke. In this model, gravity is not solely the curvature of spacetime by mass and energy. There is an additional dynamic scalar field that permeates the universe, a kind of background energy that influences how gravity works on large scales. When you plug a wormhole into the equations of Brans-Dicke theory, something fascinating happens. The need for exotic matter at the throat can be reduced or, under very specific conditions, even eliminated. The extra scalar field can provide some of the repulsive push needed to hold the tunnel open, taking pressure off the requirement for bizarre quantum materials. It is as if the universe itself provides a kind of anti-gravity background radiation that we could, in principle, harness. More recent work in string theory and brane cosmology paints an even more dramatic picture. Our universe in these models might be a three-dimensional membrane floating in a higher dimensional space. A wormhole in our world could be the shadow of a gravitational funnel that dips through these extra dimensions, re-emerging far away. In such a higher dimensional landscape, the severe energy conditions that forbid traversable wormholes in 4 dimensions might be relaxed. Ordinary matter, threaded through these extra spatial directions, could create stable tunnels without violating the known laws of physics as we experience them. The implications are profound. If a traversable wormhole can be supported by normal or only mildly exotic matter, it transforms the concept from a fantastical engineering nightmare into something that might occur naturally or be within the distant reach of a sufficiently advanced civilization. We would no longer need to manufacture a star's worth of quantum ghosts. We might instead learn to sculpt spacetime using forces and fields that are already part of the cosmic tapestry, just waiting to be understood. The search is not for a magic material, but for a deeper set of blueprints, a more complete theory of gravity that shows us how the universe truly bends. Finding such a theory would not just give us wormholes, it would rewrite the story of the cosmos itself. Our universe might be a page in a much larger book. This is the breathtaking premise of brain world scenarios, a vision that emerges from the depths of string theory. In this view, the 3-dimensional space we inhabit plus time is not all there is. It is a membrane, or brain for short, a kind of cosmic sheet floating within a grander, higher dimensional arena called the bulk. We are confined to our brain like characters living on the surface of a painting, unable to perceive the gallery around us. But gravity and perhaps other forces can leak into the bulk, influencing other brains floating nearby. Now, place a wormhole into this multidimensional landscape. A traditional wormhole in our brain is a tunnel that stays within our sheet, bending it sharply. But a higher dimensional wormhole could be something entirely different. Picture our universe again as that flat sheet of paper. 2 dots are drawn far apart. In our normal space, the shortest path is the line between them. But if the paper is floating in a 3-dimensional room, you could bend the paper so the dots touch, or more elegantly, you could simply draw a line with a marker through the air, connecting them directly above the sheet. That line through the air, through the bulk, is the higher dimensional shortcut. A spacecraft would not travel through a tunnel in our space, but would briefly detour out of it into the extra dimensions before re-entering at the destination. This detour through the bulk could be vastly shorter than any path constrained to the brain. Why does this matter for the exotic matter problem? The severe energy conditions that demand negative energy to hold a 4-dimensional wormhole open are derived from Einstein's equations in our 4-dimensional spacetime. But gravity in the bulk could obey different or more relaxed rules. The intense curvature needed for a short cut might be achieved by the gravitational influence of other brains, or by the geometry of the bulk itself, without requiring us to line the tunnel with impossible quantum materials. It shifts the engineering challenge from manufacturing exotic matter to understanding and then navigating the hidden geography of higher dimensions. The wormhole is no longer a door in a wall. It is an elevator that briefly leaves the building, offering a view of the city from above before arriving at the skyscraper across town. The universe's potential immune system works through a terrifyingly elegant feedback loop. To understand it, we must zoom into the quantum realm once more, where particles are not just tiny balls but also waves of probability. When a particle approaches a wormhole tuned to be a time machine, its path can become a twisted knot. It travels through the wormhole, emerging in the past, only to then travel forward in normal time and re-enter the wormhole again, meeting its earlier self. In the bizarre logic of quantum mechanics, this is not 2 separate particles colliding. It is the same particle interfering with its own probability wave. Every time this loop completes, the wave's amplitude, its effective size or probability, gets added together. In a stable spacetime, these amplitudes might cancel out or remain finite. But in the unstable geometry of a near-time machine, they reinforce each other. the particle's probability wave begins to resonate with itself like a microphone placed too close to a speaker. The screeching feedback builds louder and louder with each pass through the loop. In the equations, this resonance does not reach a limit, it spirals toward infinity. An infinite buildup of quantum energy in a finite region of space is a recipe for cosmic catastrophe. This energy would violently warp the local geometry, overwhelming the delicate structure holding the wormhole open. The tunnel would either collapse into a singularity or simply tear itself apart in a flash of radiation, erasing the time loop from existence before any macroscopic paradox could ever occur. This is the universe's fail-safe, a law written into the quantum fabric. It suggests that time travel to the past is not merely difficult or dangerous, but fundamentally toxic to reality. The moment the conditions for a paradox begin to crystallize, physics itself reacts with overwhelming force, sterilizing the timeline to preserve cause and effect. It is a cosmic immune response, eliminating the temporal infection by destroying the gateway that made it possible. That cosmic immune system protects the timeline by destroying any bridge to the past. But what if we could use the bridge itself as a tool? The profound link between wormholes and quantum entanglement, the ER=EPR idea, opens a door to a future application that sounds like pure science fiction. It suggests wormholes might one day become the ultimate processors, the foundation for a computer that calculates not with electrons, but with the geometry of the universe. This is the theory of wormholes as quantum computers. To grasp this, we first need to understand the power and the problem of a standard quantum computer. Today's prototypes use qubits, quantum bits that can be in a state of 0, 1, or both at the same time, a property called superposition. They also harness entanglement, that spooky link where qubits share a state across a distance. This allows them to explore many possible solutions to a problem simultaneously, offering staggering speed for specific tasks like breaking encryption or simulating complex molecules. But there is a catch. Quantum systems are incredibly fragile. The slightest interference from the outside environment, a stray photon or a vibration, can cause decoherence, collapsing the delicate quantum state and ruining the calculation. It is like trying to balance a pencil on its tip in a hurricane. Now enter the wormhole. According to ER=EPR, an entangled pair of particles is connected by a microscopic wormhole. A complex network of entanglement, like the kind needed for advanced quantum computing, would therefore be a complex network of these spacetime threads. What if, instead of trying to protect fragile qubits in a supercooled lab, we could stabilize and enlarge one of these spacetime networks? We could grow a single macroscopic wormhole whose internal geometry is not a simple tunnel, but a complex sculpted labyrinth. The state of this quantum computer would not be stored in easily disturbed particles. It would be encoded in the very shape of spacetime within the wormhole's throat. Manipulating the computation would mean carefully tweaking the curvature of this region, perhaps by applying precise energy pulses to different parts of the structure. The calculation would proceed as the geometry itself evolves, following the laws of quantum gravity. Because the information is woven into the fabric of the universe, it would be inherently protected from decoherence. You would not be fighting the environment, you would be using the ultimate isolated system, a self-contained pocket of reality where the rules of quantum mechanics and gravity are one and the same. The processing power of such a device is almost incomprehensible. A classical computer solves problems step by step. A standard quantum computer explores many probabilistic paths at once. A spacetime geometry computer could, in theory, process information by evaluating the configuration of an entire universe of possibilities in a single topological instant. It would not just be faster, it would be solving problems in a fundamentally different dimension, quite literally. the output might be read by measuring the final, stable geometry of the wormhole, or perhaps by what emerges from its other end. This is not a machine you would build on a desk. It is a cosmic-scale mainframe, a piece of astronomical engineering that uses the universe's own deepest laws as its circuitry. It suggests that the ultimate computer may not be something we build from silicon, but something we cultivate from the quantum foam, a living equation carved into the heart of spacetime. The universe's most powerful computer might be built from the threads of its own birth. To understand that origin, we must look back to the very first moment, to the singularity we call the Big Bang. For decades, this was considered the ultimate beginning, a point from which space and time themselves emerged. But what if the Big Bang was not the start of everything, but an event within a far larger, older reality? This leads us to a radical reimagining of creation, where wormholes are not features of the universe, but its very architects. Some cosmologists propose that our cosmos did not explode from nothing, but was born from a tunnel. In this model, the Big Bang was the violent eruption of a white hole. Picture a parent universe, ancient and vast. Within it, a massive wormhole forms, perhaps from the collapse of a supermassive star or a quantum fluctuation in the cosmic foam. One end, the black hole mouth, remains anchored in that parent cosmos. The other end, the white hole, does not open into the parent universe. Instead, it becomes the seed of a new one. The moment this white hole forms, it begins spewing out matter and energy not into the space around it, but into its own newly inflating spacetime geometry. That initial hyper-fast eruption of energy from the white hole's throat is what we perceive from inside as the Big Bang. Our entire universe, in this view, is the expanding fireball ejected from the white hole end of a primordial wormhole. We are not looking out from the origin point. We are living inside the aftermath of a cosmic birth canal. This elegantly sidesteps the philosophically troubling idea of a singularity arising from absolute nothingness. The energy and laws of our universe are inherited, funneled through the wormhole from the physics of a parent cosmos. We are a branch, a budding offspring connected by a severed umbilical cord of spacetime. An even more mind-bending variation suggests we are not outside the tunnel, but still within it. This is the universe as a black hole interior. Imagine a massive star collapsing in another universe, forming a black hole. According to some interpretations of the equations, the interior of that black hole need not be a crushing singularity. Under the right conditions, the infalling matter could trigger a rebound, a bounce that creates a new, expanding region of spacetime inside the event horizon. We and everything we see are inside that expanding region. The event horizon of that parent black hole is not a surface we can see or reach. It is the cosmological horizon of our universe, the ultimate limit of how far we can observe. In this model, every black hole that forms in our universe could itself contain an entire new cosmos, budding inward into its own dimensional space. This creates a fractal multiverse, a nesting doll of realities, each connected to its parent by a wormhole that is, from the outside, a black hole. Our Big Bang was the bounce inside someone else's collapsed star. These are not just poetic metaphors, they are serious, albeit highly speculative, attempts to answer the deepest question of all: what came before the Big Bang? The answer offered by primordial wormhole theories is simple and staggering. Before our universe, there was another universe, and the connection between them was a tunnel through the fabric of reality, a thread of causality woven from gravity itself. Our cosmic history may not be a single book, but a library, with each volume connected by passages written in the language of singularities. A star that defies the very timeline of the cosmos might be a gateway in disguise. Among the countless points of light in our sky, astronomers occasionally find anomalies that stubbornly resist all conventional explanation. There are stars, like the famous Methuselah star in our own galaxy, that appear to be older than the universe itself, a logical impossibility under our standard models. Others exhibit bizarre chemical compositions or flicker in ways no normal fusion engine should. One radical hypothesis suggests we are not looking at stars at all, but at something infinitely stranger, the luminous mouths of wormholes. This is the wormhole stars concept. If a traversable wormhole exists, its entrance is not a dark, empty void. To be stable and accessible, theory suggests it must be held open by immense forces, and those forces would interact violently with the surrounding environment. Imagine a spherical mouth, perhaps the size of a giant star, floating in interstellar space. It would be a region of extreme spacetime curvature, but not an event horizon. Matter from nearby gas clouds, stray asteroids, or even a companion star could be pulled toward it by gravity. But instead of vanishing into a black hole's darkness, this material would slam into the exotic boundary of the wormhole throat at relativistic speeds. The result would be a titanic release of energy, a continuous, violent accretion shock that could glow with the brilliance of a star. From thousands of light years away, our telescopes would see a point source of light, a star like any other. But its light would tell a different story. A normal star's light comes from nuclear fusion in its core, producing a specific spectrum of elements. The light from a wormhole mouth would be the chaotic glow of superheated plasma crashing against a spacetime boundary. Its spectrum would be a messy, broad continuum, possibly lacking the clear chemical fingerprints of a true stellar atmosphere. It might flicker unpredictably as chunks of matter of different sizes fell in. The most tantalizing signature, however, would be in its gravity. All massive objects bend light, but a wormhole mouth would do so in a unique way. A black hole, when it passes in front of a distant star, creates a phenomenon called gravitational lensing, where the star's image is distorted into a ring of light, an Einstein ring. But at the center of that ring lies the black hole's shadow, the dark silhouette of its event horizon from which no light escapes. A wormhole mouth has no event horizon. It is a gateway, not a prison. Therefore, if it lends the light of a background star, you would still see a bright ring of distorted light, but the center might not be dark. You might see a second, distorted image of the background star, or a strange, shimmering pattern caused by light taking multiple paths through the wormhole's twisted geometry. It would be a lensing ring with a ghost at its center, not a shadow. Finding such an object would require painstaking analysis of millions of stellar images, searching for that one perfect alignment and that one impossible signature. It is a cosmic needle in a haystack, yet if we ever found a star that cannot possibly be a star, one that winks at us with the light of a shattered reality, we may have found not a sun but a door. The universe's most profound structures might have been forged in its first frantic breath. To find a stable wormhole, we may not need to build one. We might simply need to look for a fossil from the era of cosmic inflation. This is the period, a fraction of a second after the Big Bang, when the entire observable universe expanded from smaller than a proton to the size of a grapefruit, faster than the speed of light. This hyper-expansion was driven by a mysterious energy field called the inflaton field. For that fleeting moment, the inflaton field dominated everything, filling space with a repulsive gravity so powerful it blew the cosmos apart. Now consider what this incredible energy could do to the quantum foam. In that seething, energetic chaos, microscopic wormholes were constantly bubbling into existence. Under normal conditions, they would vanish instantly, but during inflation, the physics was anything but normal. The inflaton field, with its intense repulsive gravity, could have acted as a natural source of exotic matter. As a microscopic wormhole formed in the quantum frenzy, the inflaton field's energy could have flooded into it, propping its throat open against collapse. It would be like a bubble in molten glass being instantly frozen into place as the glass cools. The rapid expansion of space itself would then have stretched these stabilized wormholes, pulling their two mouths far apart. One mouth might have been carried to one region of the universe, the other mouth hurled to a region billions of light years away, all in an instant. When inflation ended and the universe transitioned to the slower, more familiar expansion we see today, these wormholes would have been locked into the cosmic structure. They would be inflationary relics, cosmic shortcuts woven into the fabric of reality during its most violent growth spurt. They would not be tunnels we could see. Their mouths would be microscopic, perhaps still at the Planck scale, or maybe inflated to a larger but still subatomic size. They would be threads in the tapestry, connecting points that seem impossibly distant on our maps. Finding evidence for such a thing seems impossible, but cosmology offers a clue. The pattern of the cosmic microwave background, the afterglow of the Big Bang, is a snapshot of the infant universe. Tiny temperature fluctuations in this ancient light are the seeds of all future structure, galaxies and clusters. Some theorists suggest that if an inflationary wormhole connected two vastly separated regions in the early universe, it could have allowed energy and information to equilibrate between them faster than light could travel through normal space. This could leave a subtle, correlated pattern in the microwave background, a kind of statistical handshake between 2 points on the sky that should have never been in contact. It would be a ghostly signature of a connection that predates the universe as we know it. If such wormholes exist, frozen in time since creation, they transform our view of the cosmos. The universe would not be a vast emptiness punctuated by isolated islands of matter. It would be a network, a complex web of invisible threads stitching the cosmos together from its first moments. The longest journey between 2 points might not be a straight line through expanding space, but a step through a door that was hung when reality was still taking its first breath. The cosmic microwave background holds echoes of connections older than light, but one of the strangest connections ever proposed links every single electron in existence into a single, timeless entity. It began as a playful thought experiment from the legendary physicist John Wheeler. He once asked his student Richard Feynman why all electrons seem absolutely identical with the exact same mass, charge, and quantum properties. Wheeler's whimsical answer was because they are all the same one. He suggested there might be just a single electron in the entire universe, weaving a fantastically complex path through space and time. It travels forward in time as the familiar, negatively charged electron we know. Then, at certain points, it turns around and travels backward in time, which in the mathematics of quantum field theory appears to us as its antimatter counterpart, a positively charged positron. This zigzagging, universe-spanning world line would create the illusion of a vast sea of identical particles, when in reality it is just one solitary traveler, stitching the cosmos together with its own history. Feynman reportedly loved the idea, and it became a famous piece of physics folklore, a beautiful metaphor for the deep symmetries in particle physics. But what if this metaphor could be more than just a clever picture? Modern wormhole theory offers a breathtaking mechanism to make it physically real. The single electron would not need to magically reverse its arrow of time. Instead, its path could be channeled through a dense network of microscopic wormholes, each one a shortcut connecting different moments in time. Picture the particle's world line not as a single meandering thread, but as the central strand in an immense multidimensional spiderweb. Every time it needs to appear as a positron from our forward-moving perspective, it simply takes a side tunnel through a wormhole that loops back to an earlier moment. From our point of view in linear time, we would see an electron vanish here and now, and a positron appear there and then, never realizing they are two glimpses of the same object passing through a hidden door in time. This wormhole network would act as the infrastructure for the one-electron universe, a topological framework that makes Wheeler's poetic idea a geometric possibility. It unifies the quantum field, where particles are excitations, with the topology of spacetime, where connections define reality. The eerie perfection of every electron could be a signature not of a factory standard, but of a single cosmic traveler, forever retracing its steps through a labyrinth of its own making. The single electron's journey through a wormhole web hints at a reality built from loops, not smooth fabric. To truly understand such a structure, we must move beyond Einstein's beautiful equations and confront the unfinished quest of modern physics, the search for a theory of quantum gravity. One of the most promising contenders is called loop quantum gravity. While string theory proposes extra dimensions and vibrating strings, loop quantum gravity takes a different, radical approach. It suggests that space itself is not continuous and infinitely divisible. It is granular, woven from tiny, finite loops of gravitational field. Picture the fabric of spacetime not as a smooth silk sheet, but as a chainmail tunic, with each interlocking ring representing the smallest possible unit of area and volume, a billion times smaller than an atom. This granularity has a profound consequence for the most destructive places in the cosmos. In Einstein's general relativity, the heart of a black hole is a singularity, a point of infinite density where the laws of physics break down and our equations scream in protest. But in the granular world of loop quantum gravity, there is no such thing as infinite density. The tiny loops of space can only be squeezed so tight. When matter collapses toward the center of a black hole, it reaches a point of maximum possible compression, and then it rebounds. This is the quantum bounce. Instead of a dead-end singularity, the collapse reverses. The inward-falling spacetime geometry bounces outward into a new region of expansion. From our perspective outside the black hole, we see only the event horizon and the one-way trip inward. But from the perspective of the matter itself, it is not destroyed. It passes through a cosmic bottleneck, a Planck-scale bridge, and emerges into a new, expanding universe on the other side of the bounce. That bridge is a wormhole. In this model, every black hole in our universe could be the white hole birth canal of a new cosmos. This offers a stunningly elegant resolution to the infamous black hole information paradox. The paradox asks, when matter-carrying information falls into a black hole that eventually evaporates via Hawking radiation, is that information lost forever, violating a sacred principle of quantum mechanics? The loop quantum gravity wormhole provides an escape route. The information is not lost inside a singularity. It is carried through the quantum bounce wormhole and encoded into the structure of the newborn universe on the other side. From our isolated perspective in the parent universe, the information seems to vanish behind the horizon, but in the full multiverse picture, it is preserved. It has simply emigrated. This transforms black holes from cosmic trash compactors into cosmic nurseries. The terrifying endpoint of gravity becomes a genesis point. The wormhole here is not an engineered tunnel lined with exotic matter. It is a fundamental feature of quantum spacetime geometry, a natural consequence of space having a smallest possible size. The universe prevents its own destruction by turning collapse into creation, using a wormhole as the pivot point between death and rebirth. If this theory is correct, then the night sky is not just dotted with graves for stars, but with glowing portals to infinite realities, each one a universe in its own right, connected to us by a thread of rebounding spacetime. Loop quantum gravity offers one path to a universe born from a bounce, but the other great contender in the quest for quantum gravity paints a vastly different, yet equally fertile, picture for wormholes. String theory does not propose that space is made of loops. Instead, it suggests the fundamental ingredients of reality are unimaginably tiny, vibrating strings. The pitch and resonance of a string's vibration determine whether it manifests as an electron, a quark, or a photon. But for this elegant symphony to produce the physics we observe, the strings must vibrate in more than the three spatial dimensions we experience. They require extra dimensions curled up into shapes so small we never notice them. These shapes are known as Calabi-Yau manifolds. To grasp their role, think of our familiar three-dimensional space as a long, straight highway. The extra dimensions are not other highways running parallel. They are like the intricate internal geometry of the asphalt itself, a complex microscopic landscape of tunnels, handles, and holes woven into every single point along the road. A Calabi-Yau manifold is that hidden landscape, a multidimensional shape of stunning complexity. Its topology, the way it folds and connects onto itself, is not smooth. It is filled with holes, tunnels, and bridges at the quantum scale. Some of these topological features within the extra dimensions are mathematically identical to wormholes. In string theory, a wormhole might not be a tunnel bored through our large, familiar space. It could be a structure that already exists, pre-installed in the curled-up geometry of the extra dimensions at every point. To travel from one star to another, a string wouldn't move the long way across the galactic highway. Instead, it might dip into one of these multidimensional handles at its location, travel through the shortcut within the Calabi-Yau shape, and re-emerge into our familiar space at a distant point. The journey happens through the hidden architecture that underpins reality itself. This framework also provides a potential microphysical description for the exotic matter that stabilizes a wormhole's throat. In string theory, what we perceive as different particles and forces are all manifestations of vibrating strings. The negative energy density needed for a traversable wormhole could arise from a specific configuration of these strings and the fields associated with them. Certain vibrational states, or the interplay between strings and higher dimensional objects called branes, could naturally exhibit repulsive gravitational effects. The exotic matter is no longer a mysterious, hypothetical substance. It becomes a particular arrangement of the universe's most basic building blocks, a symphony of strings playing a chord that pushes space outward instead of pulling it in. String theory thus offers a universe inherently rich with wormhole potential. They are not accidents to be engineered, but features embedded in the blueprint of space-time, waiting in the compactified dimensions for the right conditions to unfold into the macroscopic world we could one day step through. The quantum foam's fleeting whispers offer a blueprint, but the work of creation belongs to a civilization of cosmic architects. This is the theory of the bootstrapped wormhole, a step-by-step engineering manual for building a cosmic shortcut from the ground up. The first task is not construction but capture. Our far future engineers must devise a technology capable of probing the Planck-scale, the seething quantum foam where virtual wormholes blink in and out of existence trillions of times per second. They are not looking for a finished tunnel, but for the faintest topological twitch in the fabric of space-time, a signature of a wormhole seed as it briefly borrows energy from the vacuum. The moment one is detected, the impossible precision begins. They must inject a pulse of energy into that exact point, at that exact instant, to prevent the seed from repaying its quantum debt and vanishing. It is like trying to catch a single, specific raindrop in a hurricane using a needle. Success means they have stabilized a wormhole with a throat diameter smaller than a proton, a knot in reality now held permanently open. This microscopic bridge is their foundation. The next phase is growth. The infant wormhole is unimaginably fragile, held open by a thread of exotic matter generated by the capture process itself. To expand it, they must begin a process of gentle, sustained feeding. Imagine trying to inflate a balloon made of the thinnest possible soap film, where the slightest uneven pressure will cause it to pop. They cannot simply blast it with energy. Instead, they must carefully inject additional exotic matter, the repulsive gravity scaffolding, into the wormhole's walls in perfect spherical symmetry. As the throat widens from proton size to atom size to virus size, the required precision only increases. The energy costs are beyond staggering. To grow a wormhole to a mere 1 meter in diameter, some estimates suggest you might need to convert the equivalent mass of Jupiter into pure, engineered exotic energy. This is not a power plant project, it is a stellar-scale endeavor, manipulating the fundamental fields of the universe with the delicacy of a watchmaker. The entire process is a breathtaking paradox of scale, requiring godlike power wielded with subatomic finesse. It is the ultimate bootstrap operation, pulling a traversable gateway into existence by its own theoretical shoelaces, starting from nothing but a flicker in the quantum dark. The silence of the cosmos is one of its greatest mysteries. If the universe is so vast and ancient, where is everyone? This is the Fermi paradox, the unsettling question of why we see no signs of other civilizations. Wormholes offer a radical and elegant answer. Imagine a species that reaches a technological plateau far beyond our own. After mastering their star system, they face the same daunting barrier we do, the interstellar gulf. Building giant starships for century-long voyages is a primitive, wasteful solution. The true mark of a mature civilization would not be conquering the distance between stars but erasing it. They would graduate from ships to shortcuts. Their great project would not be an armada, but an infrastructure, a network of stable wormholes connecting star to star, planet to planet. This network would be their subway system for the galaxy. Once established, there would be no need for the spectacular, energy-intensive displays we might look for, like Dyson spheres or fleets of slower-than-light vessels. All travel and transport would happen instantaneously through these hidden corridors. Their presence would be subtle, their footprint minimal. We do not see them because they are not out there, lumbering across the void in ships we could detect. They are using the doors, not the hallways. Their entire civilization could be threaded through a labyrinth of tunnels woven into space-time itself, a cosmic internet of connected worlds. Their communications would not be radio waves leaking into space, but signals passed directly through wormhole channels, leaving no trace in the interstellar medium. Their energy use would be focused on maintaining the network, not on propelling mass across light years. From our limited vantage point, scanning the skies for radio signals or infrared signatures of megastructures, their galaxy-spanning society would be virtually invisible. It is the ultimate cosmic stealth technology, not by hiding their emissions, but by transcending the medium through which we search. The wormhole network theory suggests the universe may not be empty at all. It could be teeming with life, existing in a layer of reality just beneath our perception. A bustling subway of civilizations we cannot hear because we are still standing on the street, listening for the clatter of horse-drawn carriages. The violent embrace of two neutron stars might forge more than gold and black holes. These city-sized corpses of dead suns, each so dense a teaspoon of their material would weigh 1 billion tons, represent matter at its most extreme. When their mutual gravity finally pulls them into a final, decaying orbit, they do not simply crash. They spiral inward at a significant fraction of light speed, their surfaces tearing apart in a maelstrom of neutrons and magnetic fields trillions of times stronger than any magnet on Earth. In that final millisecond before they merge, the combined object reaches densities that defy comprehension, a state of matter we can only describe as a quark-gluon plasma, where the very protons and neutrons dissolve into their constituent particles. Within this seething, hyper-dense fireball, the fabric of spacetime is not just bent, it is wrung like a wet towel. Some models suggest that in this fleeting, cataclysmic instant, the geometry does not proceed smoothly to a black hole. Instead, the extreme torsion could pinch spacetime into a different topology, forming a transient throat, a wormhole that exists for a mere quantum of time before the overwhelming gravity wins and it collapses into a singularity. This would not be a traversable tunnel. It would be a cosmic spasm, a wormhole that flashes into existence and is gone in less time than it takes light to cross an atomic nucleus. The question is, could this ghost leave a fingerprint on the events we can observe? When neutron stars merge, they do not do so quietly. They announce their death with a symphony of signals across the electromagnetic spectrum, a brilliant flash called a kilonova that forges heavy elements like gold and platinum. More importantly, they scream their final moments in gravitational waves, the ripples in spacetime first detected in 2017. The gravitational wave signal from a neutron-star merger has a very specific fingerprint, a rising chirp that ends abruptly as the two objects become one. If a transient wormhole formed in that final moment, the signal might not cut off so cleanly. The newborn wormhole, even for a microsecond, would have its own unique vibrational modes. As it shuddered and collapsed, it could ring spacetime like a bell, adding a faint, high-frequency echo or a subtle distortion to the very end of the gravitational wave chirp, a dying quiver in the fabric of reality. Separating this hypothetical echo from the noise of the violent merger and the subsequent ring-down of the final black hole is a monumental challenge for our detectors. It is like trying to hear the specific crack of a single twig in the sound of a forest collapsing. Yet, as our observatories grow more sensitive, we listen not just for the crash, but for the whisper of the shape it leaves behind. Each neutron-star collision we detect is not just the creation of precious metals or a new black hole. It is a laboratory testing the absolute limits of space-time, probing whether under the most extreme pressure the universe can, for a heartbeat, stitch itself into a shortcut before succumbing to the dark. The violent dance of neutron stars tests the limits of spacetime's flexibility, but another concept bends those rules in a completely different way. While a wormhole is a static tunnel you step through, the Alcubierre warp drive is a moving pocket of space you ride within. Proposed by physicist Miguel Alcubierre in 1994, it offers a vision of faster-than-light travel that feels more like sailing than stepping through a door. Imagine a small, flat region of normal space containing a spacecraft. Now, picture the spacetime immediately in front of this region being powerfully compressed, pulling the destination closer. Simultaneously, the spacetime directly behind the region is dramatically expanded, pushing the point of origin farther away. The spacecraft itself sits inside this undisturbed bubble, a calm pocket of flat spacetime surfing on a wave of distorted geometry. It does not move through space under its own power. Instead, the fabric of space itself moves, carrying the bubble and its passenger along. The ship could, in principle, reach its destination faster than a beam of light traveling outside the bubble, because locally, inside the calm pocket, no speed limit is broken. It is like being on a moving walkway at an airport. You stand still relative to the walkway, but the walkway itself is moving, carrying you forward faster than you could walk on the stationary floor. This is the core contrast with a wormhole. A wormhole is a fixed shortcut, a door connecting two distant points. You enter here, you exit there, with no travel time through the tunnel itself. The Alcubierre drive, however, is a vehicle. It must still traverse the distance between those 2 points, but it does so by contracting the road ahead and stretching the road behind, making the journey subjectively instantaneous for the traveler. Both ideas share a notorious requirement: exotic matter. Just as a wormhole throat needs negative energy to prop it open, the Alcubierre bubble requires a ring of this repulsive gravity substance to shape the spacetime wave, compressing the fabric in front and expanding it behind. The estimated energy cost is similarly astronomical, perhaps requiring the mass energy of an entire star. Yet the experiences inside each would be profoundly different. Inside a traversable wormhole, you might look back and see your point of origin folded into a tiny, distorted disk. Inside an Alcubierre bubble, the view would be utterly bizarre. Light from stars ahead would be blue-shifted into a blinding, concentrated point, while light from stars behind would be redshifted into near darkness. You would be encased in a bubble of warped starlight, isolated from the universe's normal flow of time. This leads to another key distinction: time dilation. In a wormhole time machine, the time difference is created by moving one mouth relative to the other. Inside an Alcubierre bubble moving at effective faster-than-light speeds, there could be severe time dilation effects between the bubble interior and the outside universe. A journey that feels like days for the crew might see centuries pass at home, a one-way trip into the future. The warp drive is not a gateway, it is a time capsule on a wave. So which path is more plausible? The wormhole is a piece of cosmic infrastructure, potentially permanent once built. The Alcubierre drive is a vehicle, offering point-to-point flexibility but requiring immense power for each journey. Both are dreams written in the language of relativity. Both demand physics we do not yet command, and both whisper that the universe might allow us to rewrite the map, if only we learn to read the instructions hidden in the fabric of nothingness. Black holes are not just gravitational monsters, they are cosmic paradoxes. One of the most vexing is the information paradox, a conflict between the two pillars of modern physics. Einstein's general relativity tells us that when something falls into a black hole, it is lost forever behind the event horizon, its information, the specific arrangement of its particles crushed into the singularity and erased from our universe. But quantum mechanics has a sacred rule: information can never be truly destroyed. It can be scrambled, hidden, or transformed, but never erased. So which is right? Does the universe forget, or does it remember? The answer might be written in Wormholes. The paradox sharpened when Stephen Hawking showed that black holes are not completely black. They slowly evaporate, emitting a faint glow of thermal radiation, now called Hawking radiation. This radiation, according to Hawking's original calculation, is random and featureless, carrying no information about what fell in. When the black hole finally evaporates completely, all the information about the stars, planets, or books that formed it would be lost forever, violating quantum law. This is the crisis. One elegant resolution uses the deep connection between wormholes and entanglement, the ER equals EPR idea. Remember, a pair of entangled particles may be connected by a microscopic wormhole. Now scale that up. When a particle falls into a black hole, it becomes entangled with the hole's interior. At the same moment, due to quantum effects at the horizon, a partner particle is created and escapes as part of Hawking radiation. These two particles, the one inside and the one outside, are entangled. According to ER equals EPR, that entanglement is a wormhole, a tiny spacetime bridge. So the information from the infalling particle is not trapped inside a sealed vault. It is teleported through this labyrinth of microscopic wormhole connections directly into the structure of the escaping Hawking radiation. The radiation is not random noise after all. It is an encrypted message, a quantum telegram sent through spacetime threads containing the complete story of what fell in. From the outside, it looks like the information was burned up, but in reality, it was meticulously transmitted through the hidden architecture of quantum geometry. An even more dramatic solution involves the wormholes of loop quantum gravity, the quantum bounce we discussed. In this picture, the information never faces annihilation at a singularity. Instead, it passes through the wormhole-like bridge at the black hole's core and emerges, encoded into the very fabric of a new, baby universe. The information is not lost, it has simply emigrated to another reality. Our universe's accounting books remain balanced because the data was transferred to a new ledger. The wormhole in both these theories becomes the universe's ultimate failsafe, a cosmic escape hatch for information. It ensures that no story, no particle's history is ever truly erased. The black hole's darkness is not a tomb for information, but a tunnel to its next chapter, proving that even in the face of oblivion, the universe finds a way to remember. A black hole's paradox reveals a universe that refuses to forget. But what if the cosmos itself is shaped by emptiness? The wormholes we have imagined so far are tunnels, bridges, doors. Yet another theory strips them of their function as passageways entirely. In this view, wormholes are not shortcuts at all. They are cosmic vacuoles, bubbles of nothingness frozen into the structure of spacetime during the universe's fiery birth. Picture the early cosmos not as a smooth, expanding soup, but as a substance cooling and crystallizing. As it underwent violent phase transitions, cracks and bubbles could have been trapped within the fabric of reality, like air pockets in ice or voids in Swiss cheese. These would not be tunnels with two ends. They would be self-contained voids, regions where the local geometry of space is disconnected from our own, encapsulated within a thin shell of exotic matter or intense curvature. They are not for traveling through. They are simply there, fossilized imperfections in the crystal of creation. On the grandest scales, these embedded vacuoles would have a gravitational signature. A region of disconnected space, a bubble of void, would still have a mass associated with the energy of its boundary, but its gravity would be strange. From the outside, it might behave like a concentrated lump of dark matter, warping the paths of light and stars around it. Yet, if you could approach it, you would not find a dense object. You would find a boundary you could not cross, a surface leading not to another place, but to a self-contained pocket of geometric nothingness. This idea moves from speculation to potential evidence when we look at one of cosmology's most pressing puzzles, the Hubble tension. We have two primary ways to measure how fast the universe is expanding. One method looks at the ancient cosmic microwave background, the afterglow of the Big Bang. The other uses relatively nearby stars and supernova as cosmic mile markers. These two methods, painstakingly refined over decades, now give stubbornly different answers. The local universe seems to be expanding faster than the early universe's physics predicts. It is as if a car's current speedometer reading does not match the record of its acceleration from the moment it started moving. Something is wrong with our map of cosmic history. Could cosmic vacuoles be the culprit? If our observable universe is threaded with these hidden bubbles of void, they would affect the geometry of space through which light travels. Think of trying to measure the distance across a room filled with invisible pillars. Your laser measure would give you a longer path length as the beam detours around the unseen obstacles, even though the room's true, empty size is smaller. In cosmology, a longer apparent distance for a given amount of cosmic redshift would make it look like the universe expanded faster to create that stretch. These spacetime vacuoles, acting as permanent detours in the geometry, could trick our measurements, making the modern expansion rate seem higher than it truly is when inferred from distant objects. They would be a kind of cosmic froth, a fine structure in the fabric that complicates our simple, smooth models of expansion. We would not be living in a uniformly stretching cosmos, but in one riddled with fossilized bubbles from its first moments, each one a silent witness to a time when the laws of physics themselves were settling into place. Finding proof would require a new kind of cosmic cartography, one that maps not just the galaxies, but the subtle gravitational shadows of the voids between them, listening for the hollow echoes in the architecture of everything. Fossilized bubbles of nothingness may hide in the cosmic expansion data, but there are other ghosts that refuse to be pinned down. Within the quantum realm, where certainty dissolves into probability, even wormholes can exist in a state of pure potential. This is the concept of the ghostly wormhole, a structure that is not quite real in the classical sense, but flickers at the edge of existence, woven from the strange energy of the quantum vacuum. We have already met the Casimir effect, where two metal plates in a vacuum experience a subtle push from the seething quantum foam. That region between the plates possesses negative energy density, the exotic ingredient for a traversable wormhole. But what if that negative energy does more than just push plates? What if, in its most extreme and warped configurations, it does not merely support a wormhole, but actually is one, or at least the ghost of one? In the mathematics of quantum field theory, particles and fields can exist in states that do not satisfy the classical equations of motion. They are called virtual particles or off-shell states. They are not real, measurable objects you could catch in a detector. They are temporary fluctuations, possibilities borrowing energy from the universe, appearing and vanishing within the limits of quantum uncertainty. A ghostly wormhole is precisely this kind of entity. It is an off-shell spacetime structure. It does not satisfy Einstein's classical field equations for a stable, traversable tunnel. Instead, it is a topological possibility that pops into the quantum probability cloud, a fleeting shape in the foam that borrows enough energy to momentarily twist space into a tunnel, but not enough to become a permanent fixture of reality. It is less a door and more the idea of a door sketched in spacetime for an immeasurably brief instant. You could not fly a ship through it. It is smaller than any subatomic particle and lasts for a time so short it has no meaning in our experience. Yet, its transient existence could have subtle, cumulative effects on the quantum world. How could we ever hope to detect such an ephemeral phantom? The key is not to look for a tunnel, but for the fingerprints it leaves on the things that pass near where it might have been. If ghostly wormholes are constantly flickering in the vacuum, they would create a turbulent, foamy structure at the Planck scale. This foam would not be smooth. It would be a chaotic sea of microscopic topological changes. One proposed experiment to probe this foam involves studying the propagation of light from incredibly distant, powerful sources like gamma-ray bursts. As these high-energy photons travel across billions of light-years, their journey through this quantum foam should not be perfectly smooth. If spacetime is indeed frothing with virtual structures like ghostly wormholes, the photons should encounter subtle delays or advances depending on their wavelength, a phenomenon called vacuum dispersion. It would be like light traveling through a fog made not of water droplets, but of spacetime itself churning with possibility. Another potential signature lies in the behavior of entangled particles. If entanglement is indeed mediated by microscopic wormholes, as ER equals EPR suggests, then those wormholes are not permanent bridges. They are dynamic, perhaps flickering in and out of existence as the quantum connection is maintained. Studying the precise timing and correlations in entanglement experiments under extreme conditions might reveal statistics that only make sense if spacetime itself is participating in the connection through these ghostly structures. Observing any effect from a ghostly wormhole would be monumental. It would be a direct observational window into quantum gravity, the holy grail of modern physics. It would prove that spacetime is not a static stage, but a dynamic quantum entity where geometry itself is subject to uncertainty and probability. The universe would be revealed not as a collection of things in space and time, but as a living geometry, constantly dreaming of shortcuts in the dark, birthing and dissolving tunnels in the endless creativity of the vacuum. The quantum vacuum whispers with possibilities, but the cosmos shouts with a force far more powerful. Since the late 1990s, we have known the universe is not just expanding, it is accelerating. Galaxies are flying apart from each other at a faster and faster rate, driven by something we call dark energy. This mysterious entity makes up about 70% of the cosmos and acts as a kind of anti-gravity, a repulsive pressure stretching the very fabric of space. Its nature is one of the greatest puzzles in physics, but what if this dominant force of cosmic exile, pushing everything apart, could be harnessed to do the opposite, to build a bridge? This is the audacious idea of using dark energy to forge a wormhole. The connection lies in that key requirement, negative pressure. To hold a wormhole throat open against the crushing force of gravity, you need a substance that pushes outward, a repulsive gravity. Exotic matter provides this on a quantum scale. Dark energy, on the other hand, provides it on a cosmic scale. It is the ultimate negative pressure, permeating all of space and driving the acceleration of the entire universe. So the question becomes, could this omnipresent repulsion be somehow concentrated, focused, or manipulated? Imagine not mining exotic matter, but instead building a kind of cosmological siphon. The goal would be to draw the dark energy from a vast volume of space and funnel it into a specific region, intensifying its repulsive effect until it becomes strong enough to counteract gravity in a localized area, propping open a tunnel. Think of it like this: the air pressure in a room is uniform and gentle. but if you could somehow gather all the air from the entire room and force it into a bicycle tire, you create an intense, localized pressure strong enough to lift a car. The engineering challenge is beyond staggering. Dark energy is not a fluid we can pipe. It is a property of empty space itself, likely tied to the quantum vacuum or a dynamic field. To concentrate it, we would need to alter the fundamental geometry of spacetime on a massive scale, perhaps creating a region of such severe curvature that dark energy's repulsive effect is amplified naturally. One speculative idea involves cosmic strings, those ultra-dense relics from the early universe. The immense gravity of two cosmic strings moving past each other at near light speed could warp spacetime so severely that it not only might create a wormhole, but the process could also focus the ambient dark energy, providing the stabilizing negative pressure. The wormhole would be a child of both the universe's earliest structures and its dominant modern force. Another possibility lies in the nature of dark energy itself. If it is a form of energy that can vary in strength across space or time, there might be places in the cosmos where it is naturally more intense, perhaps near the cores of ancient galaxy clusters or in vast cosmic voids. These regions could be the universe's natural construction sites, where the repulsive pressure is already amplified, waiting for the right topological trigger to form a stable throat. Using dark energy transforms the narrative completely. Instead of fighting the universe's dominant force, which is relentlessly pushing everything apart, we would be collaborating with it. The same energy that dooms galaxies to eternal isolation could become the architect of connection. It suggests a future not where we conquer the cosmos, but where we learn to speak its language, to take the signature of cosmic exile and rewrite it as an invitation to journey. The silent galaxy around us might not be empty but fully occupied. A civilization that masters its entire galaxy, a Type 3 on the Kardashev scale, would face a problem of scale. Managing a realm of hundreds of billions of stars across 100,000 light-years is impossible with ships, no matter how fast. The only solution is to erase distance itself. Their ultimate achievement would not be a fleet but a subway map. They would construct or discover and stabilize a network of wormholes, turning the sprawling galactic disk into a neighborhood of connected gates. Each stable wormhole mouth becomes a nexus, a cosmic port of call. Planets with these natural or artificial portals would become the centers of everything, the galactic capitals, trade hubs, and cultural crossroads. Imagine a planet where the sky is dominated not by a moon, but by the shimmering, spherical mouth of a wormhole, a permanent gateway to a star system 50,000 light-years away. On its surface, beings from 1,000 different stellar environments mingle in atmospheres carefully regulated by technology. Goods that could never survive a centuries-long voyage are shipped instantaneously. A musical performance on a world orbiting a red dwarf is attended in real time by audiences from 100 blue giant systems. The flow of information, life, and resources is constant, weaving the galaxy into a single, interconnected organism. Conflict in such a network would not be about territory in the conventional sense. It would be about controlling the gates themselves. A strategic wormhole nexus, a choke point connecting entire spiral arms, would be worth more than any star cluster. Wars would be fought not across the void, but at the thresholds of these tunnels, with the ultimate threat being the destabilization of a gateway, severing an entire sector from the galactic community. This perspective casts our own situation in a haunting new light. Our solar system, with its single, ordinary star and its collection of rocky and gaseous worlds, might be a cosmic backwater, not because it is barren, but because it is disconnected. No stable wormhole mouth exists within 100 light-years of us. We are off the grid, a quiet village in the countryside with no roads leading to the interstellar highway. The great galactic civilization, if it exists, hums along its web of tunnels, its attention and traffic flowing through the linked stars. they have no need to send slow, detectable probes or radio signals into the vast, empty tracts between their gates. Why would they? The network is their universe. Our isolation, then, is not evidence of our uniqueness or of a barren cosmos. It could simply be a matter of poor cosmic real estate, a quiet corner of the galaxy where the space-time geometry never formed a convenient door, leaving us to gaze at the silent stars and wonder why we seem to be alone. Our isolation might be a matter of disconnected geography, but the ultimate connection could be to the observer within. The strangest frontier in quantum mechanics is not a place, but a process, the mysterious jump from probability to reality known as the collapse of the wave function. In the classic double-slit experiment, a single electron fired at a barrier with two slits behaves like a wave, passing through both openings and interfering with itself to create a pattern on a screen. But the moment a detector is placed to observe which slit it goes through, the electron snaps into a single, definite path, acting like a particle. The act of measurement, of observation, seems to force the quantum world to make a choice. For decades, physicists have debated what constitutes a measurement. Is it the physical detector, or is it the consciousness of the scientist who reads the detector's output? This is the hard problem of measurement, and it places consciousness in a bizarrely central role in the creation of reality. Now, extend this to the most twisted geometry imaginable, a traversable wormhole. Its very stability depends on a delicate balance of quantum fields and exotic matter, a system of immense complexity. Some highly speculative theorists propose that such a structure, which fundamentally entangles cause and effect and creates closed loops in time, might not be a passive object. It could be an active participant in the quantum process. Could the act of traversing a wormhole, of sending information through a loop where effect can precede cause, require a conscious observer to resolve its inherent paradoxes? The idea suggests that consciousness might not just observe reality, but in extreme conditions might be necessary to stabilize it. A wormhole could be a bridge that only exists in a definite state when a mind is present to navigate its contradictory possibilities, forcing the quantum foam of its structure to crystallize into a stable tunnel. This ventures far beyond physics into the realm of philosophy and even mysticism. It echoes ancient ideas of reality as Maya or illusion, and modern psychedelic experiences where users report sensations of transcending space and time, of perceiving the interconnectedness of all things. Could these altered states be a fleeting, subjective glimpse into a topological truth, a feeling of the wormhole web that underlies reality? If consciousness and space-time are deeply linked, then a wormhole might not be a tunnel through the stars, but a tunnel through perception itself. It becomes a bridge not just between 2 points in space, but between the objective universe and the subjective mind that perceives it. Stepping through could be less a physical journey and more an expansion of awareness, emerging with the geometric fabric of existence. While firmly in the realm of fringe science, this theory challenges our deepest assumptions. It asks if the universe's greatest shortcuts are waiting not in the dark between galaxies, but in the luminous dark within us, in the observer that turns the quantum maybe into the definite here and now. Gravitational waves are the universe's most honest messengers, carrying truths written in the vibrations of spacetime itself. We have learned to listen to the violent crescendo of black holes merging, a signal that rises to a peak and then fades. But what would a stable, traversable wormhole sound like? Its song would be utterly different, not a collision but a resonance. Imagine striking a giant cosmic bell. The sound it makes is not a single note but a complex blend of frequencies, a ringing that slowly fades as the vibrations dissipate. A wormhole's throat, held open by exotic matter, would behave in a similar way. It is not an event horizon, a one-way membrane. It is a dynamic structure, a region of extreme curvature with its own set of natural vibrational modes. When something passes through it, a star, a dense cloud of gas, or even another gravitational wave, it would not simply vanish. It would excite the throat, setting this cosmic bell into motion. The wormhole would ring. This ringing would manifest in the gravitational wave signal as a series of precise, decaying echoes after the main event. If a small black hole were to oscillate back and forth through the throat, or if two gravitational waves from unrelated cosmic crashes entered opposite mouths and interfered inside, the resulting signal would not be a clean chirp. It would be a messy, resonant hum, a fingerprint of the tunnel's specific shape, size, and the exotic matter holding it open. Detecting this whisper requires a new kind of ear. Ground-based observatories like LIGO are superb at hearing the high-frequency crashes of stellar mass black holes. But the low, deep hum of a macroscopic wormhole, with a throat perhaps millions of kilometers wide, would vibrate at frequencies too low for these instruments. This is where the future arrives in the form of a space-based detector called LISA, the Laser Interferometer Space Antenna. Planned for the 2030s, LISA will consist of 3 spacecraft flying in a giant triangular formation, millions of kilometers apart, connected by laser beams. It will be sensitive to the low-frequency gravitational waves that rumble through the cosmos, the domain of supermassive black holes and just possibly stable wormholes. Floating in the quiet of space, free from Earth's seismic noise, LISA could listen for the resonant ring of a cosmic throat. The data would appear not as a simple spike, but as a specific pattern of spectral lines, like a barcode identifying not a mass but a topology. Finding it would be the first direct evidence that spacetime can be threaded into a permanent shortcut. We would move from hunting for shadows to listening for architecture, hearing the universe's hidden geometry sing its own strange, stable song. The resonant song of a wormhole would be a vibration in spacetime, but what if the tunnel itself is not what we think it is? To understand its true nature, we must confront one of physics' most radical ideas, the holographic principle. This principle suggests a profound and unsettling truth about reality. All the information contained within a 3-dimensional volume of space, every star, every planet, every atom inside it, can be perfectly described like a hologram on its 2-dimensional boundary. The universe we experience in 3 dimensions is a projection, a cosmic illusion generated from information encoded on a distant surface. Think of it like watching a 3-dimensional movie. The rich, immersive world you see is not truly inside the theater. It is all contained on the flat, 2-dimensional surface of the screen. The holographic principle says our cosmos is that movie, and the screen is the boundary of space itself. Now place a wormhole into this holographic cosmos. According to this view, the wormhole you see, the 3-dimensional tunnel connecting 2 distant points, is not the fundamental object. It is also a projection. The real connection happens on the 2-dimensional boundary. Imagine 2 separate, distant regions on that cosmic screen. On that flat surface, these 2 regions become deeply entangled in the quantum sense. Their information is linked. In the holographic dictionary, that quantum entanglement on the boundary translates directly into geometry in the projected 3-dimensional world. The physical manifestation of that deep informational link is a bridge, a wormhole. The 3-dimensional tunnel is the geometric echo of a 2-dimensional quantum handshake. This transforms a wormhole from a piece of cosmic plumbing into something far more abstract and powerful, an information-theoretic structure. It is not primarily a tunnel through space. It is a physical representation of shared knowledge between 2 distant parts of the universe's code. The exotic matter holding it open, the curvature of its throat, all these physical properties become secondary effects, shadows cast by a primary connection of data. This provides a stunning new perspective on the ER equals EPR idea we explored earlier, where entanglement equals a wormhole. The holographic principle gives that equation a home. It tells us where that entanglement lies on the boundary and how it projects into our world as a tunnel. A traversable wormhole, then, would be a monument to the ultimate form of communication, not faster than light signals, but a permanent, geometric fusion of information between 2 points in the cosmic data set. It suggests that to build a wormhole, we might not need to bend space at all. We might need to learn how to write a specific, profound connection into the universe's source code on the 2-dimensional surface from which all reality emerges. A stable wormhole might not be eternal. The very quantum processes that could make it possible may also contain the seeds of its slow decay. This is the wormhole evaporation problem, a cosmic parallel to the fate of black holes. Stephen Hawking's great insight was that black holes are not completely black. Due to quantum effects at their event horizons, they emit a faint thermal glow of particles, now called Hawking radiation. This process siphons energy from the black hole, causing it to slowly lose mass and over trillions upon trillions of years evaporate away into nothingness. A traversable wormhole held open by a delicate shell of exotic matter faces a similar existential threat. Its throat is a region of extreme spacetime curvature, and wherever you have such intense geometry, you have a seething quantum vacuum. Virtual particles will constantly flicker into existence at the throat's boundary. Normally, these particle pairs annihilate instantly, but in the warped gravitational field, one particle of the pair could fall into the negative energy region of the exotic matter, while its partner escapes into the outside universe. The escaped particle carries away positive energy which must be balanced. To conserve energy, the exotic matter shell, the negative energy scaffolding, loses a tiny amount of its repulsive strength. Think of it as a slow leak in a tire. Each escaping quantum particle is a single molecule of air hissing out. The effect is unimaginably small, but over cosmological timescales it adds up. The wormhole's throat, no longer perfectly propped open, would begin a glacial process of constriction. What would this evaporation look like? There would be no dramatic explosion. From the outside, the spherical mouth would appear unchanged for eons, but a hypothetical monitor on the tunnel's internal geometry would show the throat's diameter imperceptibly shrinking year by millennium as the exotic matter's grip weakened. The journey through, once smooth and gentle, would gradually become more hazardous. Tidal forces, once negligible, would increase as the throat narrowed. Eventually, the tunnel would become too small for any macroscopic travel, then too small for light, and finally, it would pinch off entirely, severing the connection and leaving behind, at most, a burst of energy as the last of the exotic matter dissipated. For a civilization that relies on a wormhole network, this is not a theoretical curiosity. It is a critical maintenance issue. Their greatest infrastructure would have a finite lifespan, a cosmic expiration date written in quantum law. Could such decay be managed or even prevented? An advanced society might treat their wormholes like living structures requiring constant upkeep. They could develop a form of quantum irrigation, a technology to steadily replenish the exotic matter at the throat, counteracting the losses from Hawking-like evaporation. This would turn the wormhole from a static construction into a dynamic, sustained system, like a star maintained by steady fusion or a garden tended in perpetuity. The network would hum with quiet activity, not of ships passing through, but of subtle field generators and energy conduits working to reinforce the fabric of the tunnels themselves. Failure to maintain a gate would not mean immediate collapse, but a slow, irreversible strangulation of a cosmic artery. This introduces a haunting possibility for archaeology on a galactic scale. If we ever discovered the remnants of a wormhole, a structure pinched off and decaying, it might not be a natural relic. It could be an abandoned piece of infrastructure, a forgotten gateway whose maintainers vanished eons ago, leaving their bridges to evaporate in the silent dark, a monument to a civilization that mastered the stars but could not outlast time itself. The silent evaporation of a wormhole speaks to a fragile equilibrium, but some shortcuts might be forged not from stillness but from a relentless, dizzying spin. Most of the wormhole models we have explored so far are static, perfect spheres frozen in time. Yet our universe is not static. It spins. Stars rotate, galaxies whirl, and black holes especially can spin at a significant fraction of the speed of light. To describe such a dynamic cosmos, we need a more complex map. This is where the Kerr metric enters the story, a solution to Einstein's equations that describes not a simple, dead black hole, but a rotating one. Named for physicist Roy Kerr, this mathematical framework reveals a cosmos far stranger than the static models suggest. Within the Kerr metric, the crushing point singularity of a simple black hole is replaced by something utterly bizarre, a ring singularity. Picture not a dimensionless point of infinite density, but a ring, like a cosmic donut of oblivion, spinning at incredible speeds. The mathematics suggest that this ring does not simply crush everything that touches it. Due to the intense frame dragging caused by the rotation, the spacetime geometry around it becomes so twisted that pathways might exist that avoid the ring's lethal embrace entirely. This is the theoretical Kerr wormhole. Some solutions within the Kerr framework allow for the black hole's interior geometry to connect to another region of spacetime, or even another universe, via a tunnel that threads through the center of this spinning ring. The rotation itself, the relentless whirl of spacetime, could provide a form of stability that static wormholes lack, perhaps reducing the need for exotic matter. But could you actually travel through it? The journey would be a nightmare of conflicting forces. Approaching a rotating black hole, you would be caught in the current of frame dragging, spun around like a leaf in a whirlpool long before you reached the event horizon. If you survived that and navigated to the ring singularity, the tidal forces would still be monstrous, stretching and compressing your ship in multiple directions at once. Theoretically, a perfectly calculated trajectory could send you through the whole of the ring, like threading a needle with a spacecraft moving at relativistic speeds, avoiding direct contact with the singularity itself. Success would mean emerging from the other side of the ring into somewhere else. The destination is wildly uncertain. It could be another part of our universe, a different time, or an entirely separate cosmic realm. The Kerr wormhole is not a gentle, engineered Morris Thorne tunnel. It is a violent, natural cataract in the river of spacetime, a chaotic gateway born from spin rather than careful construction. Its very existence suggests that the universe's most powerful engines, spinning black holes, might not be mere endpoints. They could be dynamic junctions, their rings not just destroyers, but perhaps the most dangerous stargates of all. The spinning chaos of a Kerr wormhole offers a violent path, but a stable tunnel could be repurposed into the most powerful scientific instrument ever conceived. Imagine a particle accelerator, but one that does not rely on miles of magnetic rings buried underground. Instead, it uses the natural, extreme physics of a wormhole's throat as its engine. This is the theory of the wormhole as a particle accelerator, a cosmic collider built into the fabric of spacetime. Our most powerful human-made machines, like the Large Hadron Collider, smash protons together at velocities incredibly close to the speed of light. The energies released allow us to glimpse the fundamental particles and forces that build our universe. Yet there is a ceiling. To probe deeper, to see the quantum grain of gravity itself or the strings of string theory, we need energies trillions upon trillions of times higher. We need to reach the Planck-scale, the regime where the universe's most basic architecture becomes visible. Building a collider on Earth to reach such energies is impossible. It would need to be larger than our solar system, but a wormhole offers a shortcut of a different kind. The throat of a traversable wormhole is a region of unimaginable spacetime curvature. The energy density there, especially if lined with exotic matter, is off any human scale. By carefully injecting a stream of particles into this environment, or even sending them on trajectories that graze the throat's boundary, we could subject them to gravitational forces and energy gradients that no ring of magnets could ever reproduce. The wormhole itself becomes the accelerator. The particles would not just be moving fast, they would be moving through geometry that fundamentally alters their interactions. In that warped corridor, collisions could occur at effective energies that touch the Planck scale. We could witness particles behaving in ways predicted only by theories of quantum gravity, perhaps seeing spacetime itself quantize into loops or strings before our detectors. It would be like using a cosmic tornado to spin a top at speeds a child's hand never could. The data would not just tell us about new particles, it would tell us about the stage upon which all particles dance. This transforms the wormhole from a transportation device into a telescope for the laws of physics. The ultimate purpose of such a machine would be to answer the questions that have haunted physics for a century. How does gravity work at the quantum level? What is spacetime made of? By using the universe's own hidden architecture as a laboratory, we could run experiments that are otherwise forever out of reach. A civilization that masters wormholes would not just gain the stars, it would gain the operating manual for reality itself, written in the debris of collisions held within a self-made cosmic storm. The universe remembers, but it only moves forward. This is the great asymmetry at the heart of reality, the arrow of time. Most laws of physics, from gravity to electromagnetism, work perfectly well if you run the film backward. A planet orbiting a star in reverse still obeys Newton's laws, but our experience is starkly one way. We remember the past, not the future. An egg scrambles but never unscrambles. Entropy, the measure of disorder, always increases. So where does this universal direction come from? The answer might be written not in the laws of particles, but in the architecture of spacetime itself, in the prevalence of wormholes during the universe's birth. To understand this, we must go back to the beginning, to that state of incredibly low entropy, of exquisite order. Why was the early universe in such a special, tidy state? One provocative idea links this tidy starting point to the formation of spacetime shortcuts. In the quantum foam of the first instance, microscopic wormholes were constantly forming and pinching off. This process of topological change, of space stitching itself into knots and then untying them, may have had a preferred direction. The act of a wormhole pinching off and sealing could be an irreversible event, a one-way stitch in the fabric that increases the overall complexity of spacetime's geometry. This increase in geometric complexity could be the fundamental driver of increasing entropy. The arrow of time on this view points in the direction of more knotted, more complex spacetime topology. As the universe expanded and cooled, these wormholes froze into the fabric or evaporated, leaving behind a cosmos whose time direction was set by that initial frenzy of topological activity. The expansion itself, which was likely driven by the same inflationary energy that could have stabilized wormholes, becomes the physical manifestation of the arrow. We are carried forward on a river of expanding space that began with a burst of cosmic stitching. Now, consider what a traversable wormhole to the past would do to this elegant picture. It would create a closed loop in time, a path where effect could precede cause. This would not just be a paradox for a time traveler, it would be a catastrophic wound in the arrow of time itself. In such a loop, entropy could potentially decrease, order could spontaneously reappear from disorder, and the clear, forward direction we rely on for memory and causality would shatter. The universe's careful construction of a timeline, starting from a low entropy state and marching toward greater complexity, would be undone by a single stable tunnel to yesterday. This may be the deepest reason time travel to the past feels so forbidden. It is not merely about preventing paradoxes, it is about protecting the very structure of history, the irreversible process that gave time its direction in the first place. A wormhole to the past would not just be a door to another place, it would be an eraser for the universe's most fundamental story, the tale of its own unfolding. The universe's arrow of time was set by ancient knots in spacetime. But could we learn to tie a new knot ourselves, not with cosmic strings, but with a beam of pure light? There is a radical, experimental idea that suggests the most powerful lasers we can build might one day carve a tiny doorway into the fabric of reality. This is not about moving a wormhole mouth or stabilizing one. It is about creating one from scratch using the raw, focused fury of an electromagnetic pulse. Imagine concentrating the power output of an entire star, not for a second, but for a fleeting quadrillionth of a second, into a beam narrower than a human hair. This is the realm of the X-ray free electron laser, a machine that already exists in facilities around the world, pushing the boundaries of what we can do with light. These lasers do not produce a continuous beam. They fire pulses of X-rays so intense and so brief that they can strip electrons from atoms in an instant, flash heating matter to temperatures hotter than the sun's core. They are the sharpest scalpels we have for probing the quantum world. Now, theorists ask, what if we push them even further? What if the next generation of these devices could achieve such an insane concentration of energy that it does more than tear apart atoms? The idea is that within the microscopic focal point of such a laser pulse, the energy density could become so unimaginably high that it begins to warp the local geometry of spacetime itself. According to Einstein's equations, energy and mass are equivalent. A sufficiently dense concentration of light energy should, in principle, create its own gravitational field. In that tiny, searing point of focused photons, spacetime would not just bend, it could be pinched. The intense electromagnetic fields could create conditions analogous to the early universe's quantum foam, exciting the vacuum to such a degree that it spontaneously generates topological structures. For a duration shorter than the time it takes light to cross a proton, the warping might be severe enough to form a microscopic wormhole throat, a self-contained loop of spacetime connecting the laser's focal point back to itself. It would be a quantum wormhole, not a tunnel to another star, but a tiny, temporary knot in the continuum, born from light and dying in light. You could not send a molecule through it, let alone a ship. It would be a proof of principle, a whisper from the lab that spacetime is malleable, that with enough energy and precision, we can not just observe geometry, but sculpt it. The engineering hurdles are, of course, cosmic. The required laser intensity is far beyond anything currently conceivable, likely requiring energies we associate with particle accelerators the size of solar systems, all compressed into a single, perfect pulse. And even if we could create it, detecting such an ephemeral spacetime knot would be its own monumental challenge. We would be looking for a ghost within a flash, a topological hiccup in a fireball of X-rays. Yet the pursuit itself changes the game. It moves wormholes from the domain of astronomers and cosmologists into the realm of experimental physicists. It suggests that the keys to the cosmos might not only be found in the depths of space, but at the focus of a beam in a controlled laboratory, where we can ask the universe direct, violent questions and listen for the geometry of its reply. The universe's stability is a comforting illusion, resting on a quantum foundation more fragile than glass. Physicists have uncovered a chilling possibility about the very field that gives particles mass, the Higgs field. It might not be in its true, lowest energy state. Instead, our entire cosmos could exist in a false vacuum, a valley of stability perched precariously on a mountainside. It is metastable, seemingly solid, but a powerful enough jolt could push it over the edge. That jolt could be a high-energy particle collision in a future supercollider, a violent cosmic event, or even a random quantum fluctuation in the void. If it happens, a bubble of true vacuum would nucleate at that point. Inside this bubble, the laws of physics would be rewritten. The Higgs field would drop to its absolute lowest energy, a state with fundamentally different properties. The bubble's wall, a boundary of unimaginable energy, would expand outward in all directions at the speed of light. Nothing could outrun it. Upon contact, everything it touched, atoms, stars, spacetime itself, would be instantly and utterly annihilated, reorganized into a new reality where chemistry, life, and light as we know them could not exist. The entire observable universe would be erased, replaced by this expanding sphere of true vacuum. It is the ultimate cosmic doomsday scenario, a reset button for existence. Yet within this terrifying theory lies a sliver of impossible hope. If a civilization saw the warning signs, if they detected the nucleation of a true vacuum bubble light years away and knew its light speed wall was coming, what could they do? No ship could outpace it, no shield could block it. Their only conceivable escape would be a shortcut that does not travel through space, but away from it entirely. A traversable wormhole could be that lifeboat. The strategy would be desperate and precise. As the wall of annihilation approached, they would need to guide their entire world, or a seed of their civilization, through the throat of a wormhole whose other mouth was anchored far, far away. But not just in another star system. The destination would need to be a place completely isolated from the spreading catastrophe. This presents two haunting possibilities. First, the wormhole could lead to a region of spacetime that is causally disconnected from our universe's fate. If the other mouth existed in a galaxy so distant that the expanding true vacuum bubble, even moving at light speed, would not reach it for billions of years, it would offer a temporary refuge, a few more eons of life before the end finally caught up. The second, more radical possibility is an exit not just to another place, but to another universe altogether, one with a stable, true vacuum as its default state. The wormhole becomes an evacuation tunnel out of a doomed cosmos, a one-way exodus through a space-time bridge to a safer, younger, or more stable reality. The engineering is beyond godlike. It would require not only a stable wormhole on demand, but the prescience to know the end was coming, and the ability to move an entire civilization through the gate in the brief window before the wall of rewritten physics arrived. It casts the wormhole in its most dramatic role yet, not as a tool for exploration or communication, but as the ultimate survival mechanism, a fire escape from a universe that has become, through a random quantum accident, fatally unstable. That ultimate escape tunnel to a safer reality forces a staggering inversion of perspective. What if we are not fleeing through a wormhole but are already inside one? This theory flips the entire cosmic narrative on its head. Instead of our universe containing wormholes, our universe might be one. Imagine the Big Bang not as an explosion from a point, but as the moment we entered the throat. The initial singularity, that point of infinite density, was not the beginning of everything. It was the narrowest part of the tunnel, the pinch point we call the Big Bang, where we passed from one realm into the interior of a cosmic bridge. In this model, the larger reality is a multiverse, a vast bulk of higher dimensional space teeming with other universes, other bubbles. Our cosmos is not a free floating bubble. It is a wormhole, a tubular connection threading between two vastly larger, perhaps infinitely large parent universes in that bulk. The Big Bang was our passage into the tube. Everything we see, every galaxy, every particle, is not expanding into a void. It is traveling through the interior of this transcendent structure. The relentless expansion of the universe, the fact that galaxies are all rushing away from each other, takes on a new meaning. It is not space itself stretching from a point of origin. It is the natural, geometric flow of matter and energy moving through the widening corridor of the wormhole. We are not on the surface of an expanding balloon. We are in the current of a cosmic river flowing from one mouth toward the other. This reshapes every question about our destiny. The fate of the universe, whether it expands forever or eventually collapses, is no longer about dark energy and critical density alone. It becomes a question of the wormhole's shape. If the tunnel widens forever, we experience eternal expansion. If it eventually narrows again, we face a big crunch, a collapse into the exit throat. And what lies at the other end? One terrifying and beautiful possibility is that the far end of our universe wormhole is a black hole in another parent cosmos. We are not looking out from a beginning, we are looking back toward the entrance and forward toward the exit, both of which are singularities from an external perspective. This provides a hauntingly elegant answer to what came before the Big Bang. There was no before in a linear timeline. There was another universe. Our entire history is the journey through the bridge between them. In this view, every black hole that forms within our universe could itself be a budding wormhole to a new cosmic interior, creating a fractal cascade of realities within realities. We are not just searching for shortcuts in the cosmos. We are living within the ultimate shortcut, a bridge so vast we mistake it for home, on a journey whose destination is written in the geometry of everything we see. The universe's most profound connection might be a blueprint for its most practical shortcut. We have already seen the radical idea that entanglement and wormholes are two sides of the same coin, captured in the equation ER equals EPR. But this is not just a beautiful piece of theoretical poetry. It points toward a tangible and already functioning technology, quantum teleportation. This is not the science fiction version of teleportation, where a person vanishes in a sparkle of light and reappears across the room. This is a real, laboratory-proven protocol for moving information, the quantum state of a particle, from one place to another without it ever traveling through the space in between. Here is how it works, stripped down to its essence. You start with 3 particles. Particle A is the one whose mysterious quantum state you want to teleport, say, the specific spin of an electron. Particles B and C are a special pair created together so they are deeply entangled, sharing a single quantum existence. You take particle B and bring it to a location far away from particle A. Particle C stays with you near particle A. Now you perform a joint measurement on particle A and your local particle C. This measurement is clever. It does not tell you what the state of particle A is, which would destroy its quantum nature. Instead, it tells you how particle A and particle C are related. This act instantly collapses the entangled pair. Particle B, now isolated far away, is suddenly forced into a specific state, but it is not yet the state of particle A. The measurement you performed on A and C gives you a piece of classical information, a simple set of instructions like a 2-bit code. You send this code to the location of particle B using a radio signal, a text message, any normal, slower-than-light method. The recipient at the distant location receives the code and, based on those instructions, performs a specific operation on particle B, rotating it in a certain way. When they are done, particle B is now in the exact, identical quantum state that particle A was originally in. Particle A's state has been destroyed in the process, but its information has been recreated perfectly at a distance. The original particle A is gone, but its quantum essence has been teleported. Now, where is the wormhole? According to the ER equals EPR conjecture, particles B and C, that entangled pair you started with, are not just mysteriously linked. They are physically connected by a microscopic wormhole, a Planck-scale bridge in spacetime. The act of the joint measurement on A and C is like sending a shockwave through that bridge. The information from particle A does not travel through space. It travels through the wormhole connection between C and B. The classical code you send is just the key to unlock the information at the other end of the tunnel. The teleportation is, in the most literal sense the equations allow, sending quantum information through a wormhole. So, what about teleporting a person or a starship? The principle scales up, but the challenge becomes cosmic. To teleport a macroscopic object, you would need to entangle every single one of its trillions upon trillions of particles with a corresponding set of particles at the destination. You would then need to perform the joint measurement on the original object and your local entangled particles, a process that would, by necessity, completely disassemble the original into a cloud of unrelated data. Then you would transmit the classical instructions for reassembly across the galaxy. At the destination, using those instructions and the distant halves of the entangled pairs, a perfect replica would be reconstructed, particle for particle, quantum state for quantum state. It would be a copy, a reassembly from raw materials at the destination, not a physical journey through a tunnel you could see, but in the language of quantum information, it is the same thing. The original you would be gone, scanned into data. The new you would step out of the reconstruction chamber light years away, with all your memories and sense of self intact, having never traveled the distance. The wormhole in this scenario is not a tunnel you walk through. It is the sum total of all those countless microscopic spacetime threads, the entangled web that allows the information of your entire being to jump across the universe in an instant. Teleportation is not magic, it is engineering on the quantum fabric of reality, using the universe's own hidden wormhole network to mail yourself to the stars. The journey through a wormhole would be anything but calm. You would be traveling through a corridor of pure, warped physics, a place where the fundamental forces of nature are stretched and twisted into forms we can barely describe. This is not a serene tunnel with smooth walls. It is a maelstrom, a churning river of spacetime itself. Theorists call this phenomenon wormhole weather, and it would be the single greatest hazard of any passage. The moment you cross the threshold, you will be entering a region of such extreme curvature that normal rules break down. The exotic matter lining the throat is not a passive shell. It would be a dynamic, quantum-active boundary, likely flickering with intense energy fluxes. These fluctuations could manifest as sudden, localized gravitational surges like space-time squalls violently shaking your vessel. You might encounter spontaneous flashes of Hawking radiation, bursts of particles born from the quantum vacuum at the throat's boundary, bathing the interior in deadly, high-energy light. The most persistent danger, however, would be the tidal forces. Even in a carefully engineered, traversable wormhole, gravity would not be perfectly uniform. The pull on the side of your ship closer to the exotic matter shell would be slightly different from the pull on the far side. This difference, this tidal shear, would act like a cosmic force trying to stretch you apart lengthwise while squeezing you in from the sides. In a poorly designed or naturally occurring wormhole, these forces could be catastrophic, spaghettifying anything inside in an instant. But even in a stable one, they would create a constant, wrenching strain, a gravitational turbulence that would test the limits of any structure. Navigating this would require more than just a good pilot. It would demand a ship with active gravitational compensation, a system that could sense these space-time squalls and adjust its own local inertial field to counteract them, like a gyroscope stabilizing a ship in a stormy sea. The hull would need to be shielded not just against radiation, but against the geometry of space itself, perhaps lined with its own layer of controlled exotic matter to smooth out the worst of the tidal shears. The journey, though instantaneous in terms of external distance, would subject the crew to a subjective eternity of violent, unpredictable physics. You would not watch the stars go by. You would be fighting to hold your ship and your sanity together inside a storm made of reality's twisted fabric. Is this ferocious weather merely a hazard, or could it be a signature, the roaring proof that you are not in normal space anymore, but passing through the wound in the universe's skin? The storm inside a wormhole is not just a physical hazard, but a mirror for the moral turbulence such power would unleash. Mastering a cosmic shortcut is more than an engineering triumph. It is a societal earthquake, forcing us to confront questions that have no easy equations. The moment a stable wormhole is proven possible, the first great debate will not be about the physics, but about the politics. Who controls the gate? Is it the nation or corporation that built it, claiming it as sovereign territory? Is it an international consortium, a new United Nations for a connected galaxy? Or does such a profound piece of cosmic architecture belong to all of humanity by default? a common heritage like the high seas or outer space, the answers would define our future. A single entity controlling the only door to the stars could become an unchallengeable superpower, holding the keys to economic wealth, military dominance, and scientific discovery. They could charge exorbitant tolls, dictate who may pass, or seal the gate entirely. This is a recipe for a new interstellar feudalism where access to the cosmos is a privilege, not a right. Conversely, if the technology was shared openly, it could spark an era of unprecedented collaboration. Shared gateways could become the foundation for a truly unified human civilization, focused not on competing for resources on one world, but on exploring a million together. The wormhole becomes a test of our maturity, revealing whether we will use a tool of infinite connection to build walls or bridges, and what awaits us on the other side of those bridges. The philosophical stakes skyrocket when we consider we may not be alone. A traversable wormhole is not just a transportation device, it is an instrument of first contact, and one that arrives with terrifying immediacy. There is no decades-long radio message, no slow approach of a generation ship. One day, a shimmering sphere appears in orbit and something steps out. Or worse, we are the ones stepping out unannounced into someone else's sky. What are the rights of a civilization we discover? Do we adhere to a cosmic prime directive, observing without interfering, even if it means watching a world perish to a preventable disaster? Or does knowledge and capability bring an ethical responsibility to act? If we find a pre-industrial society on a planet rich in resources we desperately need, do we have the right to mine it, even if we promise not to disturb the natives? History on Earth suggests the powerful rarely resist such temptation. Wormhole technology could enable a new age of imperialism, not across oceans but across light years, with advanced humans becoming the alien conquerors in someone else's nightmare. To avoid this, we would need to develop an entirely new ethical framework, a galactic social contract written before we ever meet another soul, governing interaction, trade, and the sanctity of independent evolution. The gateway forces us to decide what kind of galactic citizens we want to be before we ever leave the porch. These questions of identity become infinitely more tangled when time travel enters the picture. A wormhole that allows journeys to the past does not just move bodies through space. It moves actions through time, shredding our foundational concepts of responsibility and justice. If you could go back and prevent a crime, are you responsible for the lives saved? What if your prevention inadvertently causes a worse tragedy? If someone uses a time gateway to alter a historical election, who has the moral authority to correct it? The very notion of cause and effect, the bedrock of law and personal accountability, dissolves into a fog of infinite revision. Your sense of self would fracture. Meeting a younger version of yourself is not a curiosity, it is a profound ontological crisis. Which one is the real you? Does the older version have authority over the younger? If you give your past self winning lottery numbers, are you the benefactor or the beneficiary? The easy rewriting of personal history could make life feel weightless, devoid of consequence, where every mistake is merely a draft to be edited. But a world without permanent consequences is a world without growth, without meaning, and without a coherent story. We are the sum of our irreversible choices. A time-traveling civilization might gain the stars but lose its soul, adrift in a sea of might-have-beens, forever homesick for a linear timeline where actions matter. Ultimately, the wormhole holds up a mirror to our deepest nature. It asks if we are wise enough to handle a tool that renders distance and time optional. The physics tells us what is possible, but the ethics, the philosophy, the messy business of being conscious creatures in a connected cosmos tells us what is permissible. The greatest danger posed by a cosmic shortcut is not the exotic matter or the quantum storms. It is the reflection we see in the shimmering surface of the gate, a reflection of who we were, who we are, and who we might become when the entire universe is just a step away. That moral turbulence, that profound question of who we become when we hold the fabric of reality, points toward an ultimate destiny. The mastery of wormholes may not be the final goal of a civilization, but a necessary rite of passage. It could be the universe's own test, a cosmic puberty that separates the children from the adults in the galactic community. For billions of years, life on any world is a local phenomenon. It is born on a single rock, evolves under one sun, and looks out at the stars as distant, untouchable points of light. Its struggles are planetary, its triumphs confined to a single atmosphere. It uses the resources of its cradle, builds towers to its sky, and perhaps even sends fragile probes into the void. But it is still a passive inhabitant, a spectator in a vast arena it cannot truly enter. The chasm between stars remains an absolute barrier, then a breakthrough, not just in physics but in perspective. The civilization stops trying to cross the distance and starts asking how to erase it. It turns its gaze from building faster ships to understanding the deeper blueprint, the geometry of spacetime itself. This is the pivotal moment. The pursuit of a wormhole is more than an engineering challenge. It is a fundamental shift in a species' relationship with the cosmos. It is the moment they stop accepting the universe's rules as a fixed stage and start learning how to remodel the theater. Success means graduating from a tenant to an architect. Imagine a single, shimmering gateway finally stabilized, hanging in the space above their homeworld. That sphere is more than a door, it is a symbol of maturity. It declares that this species has learned to speak the universe's most fundamental language, the mathematics of gravity and quantum fields. They are no longer bound by the geography they were born into. They have learned to knit. With that first wormhole, everything changes. Their concerns are no longer planetary but interstellar. Their economy shifts from managing the resources of a single system to the flow of goods and energy between stars. Their art, their philosophy, their very sense of identity expands to encompass multiple suns. They become, in a very real sense, a multi-stellar organism. But this is only the beginning of the journey. A single wormhole is a proof of concept. A network of them is a declaration of intent. As the civilization weaves more tunnels connecting star to star, they are not just building transportation. They are actively restructuring the connectivity of their corner of the galaxy. They are imposing a new topology on spacetime, creating shortcuts where none existed, drawing once isolated points into a neighborhood. This is the act of a cosmic gardener, tending not to plants but to the very pathways of reality. And here lies the most breathtaking possibility of this theory. What if this is not a lonely endeavor? What if the test of building a stable wormhole is the universal entrance exam for a community that has long been hidden? The galaxy may not be silent because it is empty. It may be silent because all the mature civilizations are already inside, communicating and traveling through a labyrinth of tunnels we cannot perceive. Our radio telescopes listen for shouts across the canyon, but everyone else is using the underground subway. In this vision, a species that achieves wormhole technology isn't just exploring. It is plugging into an existing network. That first successful gateway might not open onto empty space. It might connect to a central nexus, a grand terminal maintained by others who passed this same threshold eons ago. They would find not just new worlds, but new peers. The galaxy's great conversation would not be carried on radio waves, but through the shared maintenance of spacetime infrastructure, a collaborative project to keep the cosmic shortcut stable and open. This transforms the Fermi paradox from a puzzle of loneliness into a story of stages. We do not see them because we are not yet looking in the right place, and we have not yet built the right key. The silent stars are not graves, they are schools. Each one is a potential cradle where a species struggles with its own planetary adolescence, facing wars, climate crises, and technological growing pain. The ones who survive, who unify and direct their genius outward to solve the fundamental puzzle of connection, earn their place in the wider cosmos. They move from the classroom to the common room. So, the 50 theories we have explored are not just a catalogue of fantastic physics. They are a potential curriculum. From the quantum foam to dark energy, from black hole echoes to entangled particles, each concept is a chapter in the universe's own textbook on cosmic engineering. Mastering them is the final exam. The wormhole, then, is more than a tunnel. It is a diploma. It is the universe's way of saying a species is ready to move out of its cradle, not in a ship, but with a needle and thread, ready to help sew the galaxy together. The question hanging in the void is not whether such shortcuts exist. It is whether we, as a species still arguing over lines on maps, can grow up enough to learn the stitches. From the first mathematical whisper of an Einstein-Rosen bridge to the stormy ethics of a galactic subway, this journey across 50 theories has charted the outermost edges of human thought. We have seen wormholes as cosmic fossils, as quantum whispers in a lab, as the hidden stitches in spacetime that might bind everything from dark matter to the arrow of time itself. They are bridges between black holes and white holes, threads connecting entangled particles, and potential fire escapes from a dying universe. While no wormhole has ever been detected, their persistent presence in our equations is a beacon. It tells us that our map of reality is incomplete, that the universe holds geometries more wondrous than our three-dimensional intuition can grasp. The quest to understand them has become a grand unifying project, forcing gravity to shake hands with quantum mechanics and pulling cosmology into conversation with the philosophy of consciousness. Each theory, whether built on spinning cylinders or quantum foam, is not just a blueprint for a tunnel. It is a probe into the deepest laws of existence. The true value of this 50-year conversation among physicists is not that it gives us a faster way to travel. It is that it expands what we believe is possible. It teaches us that space and time are not a fixed stage, but a dynamic, malleable substance. That emptiness is alive with potential, that the past, present, and future might be woven together in a topology we are only beginning to decipher. So as you look up at the night sky, remember this: the distance between stars is not merely a void to be crossed, it is a question to be answered. The cosmos is far stranger, more connected, and more ingeniously constructed than we ever dared to dream. And our human drive to unravel its mysteries, to test these wild ideas against the stubborn bedrock of reality, is the greatest adventure there will ever be. We are all part of that story. Tell us which of these 50 doors to the impossible captured your imagination the most. Share your favorite wormhole theory in the comments below.